If you want to get started using Matlab, you're going to love this course. In it, you will learn one of the most popular programming languages for data analysis, engineering, science, and economics. Jerry and I worked with Justin to produce this course originally on Udemy, and it has since been removed, and we are going to go ahead and offer it for free on YouTube. If you would prefer more of a course-taking experience, I'll provide a link to the description to enroll in this class for free on Teachable. But it was a pleasure to partner up with Justin, who has a master's degree in computer science, and he will take you from getting started with Matlab, solving equations, analyzing data structures, plotting data, signal processing, and probability. So go ahead and give this video a like if you enjoy the content. If you want to see more content like this, feel free to subscribe, and let's get started.
Today we're going to talk about what is Matlab, how do you get it, various add-ons and toolboxes you can purchase to extend the abilities of Matlab, and generally how you can get help using Matlab. So the first thing I'm going to show you is I'm going to Google Matlab, and right at the top you see Matlab's official website. So that's where you can go to get Matlab and learn a little bit more about it just by reading on your own. To give you a short introduction though, Matlab stands for Matrix Laboratory. So if you've ever programmed before, it's a little bit different because Matlab is mostly for math, and all the variables are matrices. Even scalars are matrices. Matlab is usually used in academia and research, so if you're taking a university course which involves numerical computing, you'll probably use Matlab. If you're doing research and you're analyzing data, your professor probably already uses Matlab, and everyone in your lab, as a result, will be using Matlab. Matlab is used in fields of engineering, science, finance, and economics. At its simplest, Matlab basically does calculations, so it's a very fancy calculator. On top of that, though, you can write code to evaluate a complicated formula, you can plot equations and data, and you can implement algorithms. Okay, so let's talk about getting Matlab. So I've already opened the website. If you scroll down to the bottom, or near the bottom, you can see a section called Try or Buy. So you can try Matlab for free, probably a trial that lasts 30 days. Let's check. It doesn't say, you have to enter your email. But it's a limited time trial, so it won't last forever. If you want to buy Matlab, there are several options. So the standard Matlab you probably don't want to use. It's over $2,000. And if you're part of an educational institution, you can use the Education tab and get Matlab for $500. The home version is just for personal use. That's $149. And the student version is $49. So you probably have to go through some process to prove that you're a student. Another way that you can probably get Matlab is if you are a student at a university, there are options that the university has for you to get Matlab. So you'll have to consult with your university's resources, such as the website or the bookstore, to see if you can possibly even get it for free. For this tutorial, I'm going to be using the 2014A version of Matlab. So one thing you'll notice is for the home version and the student version is they have these add-on products that you can get for a price. So add-ons are also called toolboxes, and they have functionality and code that can be useful for you in your specific field of work. So, for example, if you do bioinformatics, you may want to purchase the bioinformatics toolbox. So you can click on the links and get an idea of what's included in the packages. Maybe you do bioinformatics and you don't really even need the functions that the toolbox comes with, so you might not want to purchase it. But in general, you can browse the documentation for free, so you can see everything that you would get if you did purchase the toolbox. It's essentially an API, so you can look at any function, see what the input and the output is, and decide if that's useful for you. The next thing I want to talk about is how to get help with Matlab. So you're already taking this course and you're going to learn a lot about Matlab here. And when you start coding, there are probably going to be some very specific things you want to do that you don't know how to do yet. So one place you can go, I clicked on the community tab on the Matlab website. And so you can see there's a community of people who use Matlab who post on this site. The file exchange I've used before. People post useful functions and code that you may need in your projects that can be useful. There's also a section called Matlab Answers where people ask questions and you can answer them, or you can ask a question and someone else can answer you. Personally, I would recommend just searching your question on Google because they've already indexed all this stuff. You could potentially put your question in the search box on the Matlab site as well, though. And you might, on Google, also get Stack Overflow results. So it wouldn't only be MATLAB Central, which might be helpful. Welcome to this MATLAB tutorial. This MATLAB tutorial is going to be on the basic syntax of MATLAB. So I've already opened MATLAB, and this is generally the screen that you see most of the time. So the big main window is called the command window. You'll be working here most of the time. You can view your variables in the workspace on the bottom left, and you can view your current directory on the top left, and so that will tell you where in the file system you currently are. So if you want to open a file from there, you don't have to type in the absolute path. You can just type in the file name directly, or if you save a file, that's where it will go. So we call that the working directory. And you can change the working directory to keep all your projects separate. So you can go into the path up here and type in another path if you want to use the path for your particular project. So in MATLAB, there are three basic types of numbers that you'll be working with, or variables, that are all actually matrices. So you have scalars, which are just plain numbers. You have vectors, which is kind of like a list of numbers. And then you have matrices, which are tables of numbers. So as I've mentioned before, in MATLAB, all these variables are represented as matrices. So if I do something like x equals 5, you see that in a regular programming language, you might just think of this as x equals 5. But I can do something like check the size of x, and I see that it's actually a 1 by 1 matrix. I can create a vector. Okay, we use square brackets, and you don't need commas, but I'm going to use them. And so that creates a vector with the elements 1, 2, 3. So if I do size of v, I see that it's a 1 by 3 vector, or you can also call it a 1 by 3 matrix. So this brings up some other interesting points about how Matlab syntax works. I mentioned that you don't actually need the commas. So we can just do that, and Matlab knows that we want a 1 by 3 matrix with the elements 1, 2, 3. So you also notice that I added this semicolon at the end of the line. And what that does, it's easier to see if I just don't do it. So it prints out the last thing. So if I don't use the semicolon, it's going to print everything out from the previous command. But if I do use the semicolon, it will suppress the output. So that's why I didn't put a semicolon after size v. If I did, I wouldn't see anything. Now we're going to go on to look at matrices. So it's very similar to creating a vector, except we need to have a way to separate each row. So that's done with a semicolon. And I'm not going to put one at the end so we can see the output. And so what that does is it creates a 2 by 2 matrix with the elements 1, 2, 3, 4 in a variable a. Right, if I do size a, it's 2 by 2. So those are the two things we've learned about initializing vectors and matrices, is that you can use commas to separate columns, but you don't need the commas. You can just use spaces. And to separate rows, you can use semicolons. Another thing is that when you're working with matrices and vectors and you're multiplying them and stuff like that, the dimensions of the vector are very important. So typically, you'd work with a column vector, not a row vector like the one I just created. And so we can easily transform the previous vector, which was a row vector, into a column vector using an apostrophe. And so that does a transpose. And so you see now that v used to be a 1 by 3 vector, and now it's a 3 by 1 column vector. You could have also initialized it using semicolons, of course. Okay, so the next thing I want to talk about is how you can access elements of a matrix. Typically, that's done using parentheses and then indices and commas in between. So if I want to, in general, access the ith row and the jth column, it would be a parentheses I comma j parentheses. So if I want A11, for example, I would do that. If I want A12, and so on. A21. Another interesting thing you can do is access a vector within a matrix. So let's say I want the first row of the matrix A. I can use the colon syntax to get the first row. So I'm going to put a 1 or I choose the row, and then I'm going to put a colon in the choice for column, which means return me all the columns in row 1. So if I do that, I get 1, 2, which is the first row of A. Similarly, I can use the colon syntax to get an entire column of A. So let's say I want to choose the second row, or sorry, the second column. So let's say I want to choose the entire second column. I would do that. And of course, if I do a colon in both parts of A, it'll just return me the entire A. So let's create a bigger matrix now, so I can better illustrate my next point. Alright, so I just created a 4x4 matrix. So the colon syntax can also be used to access ranges. So if I look at A, it's 1 to 16. If I want the part of A that has, so a submatrix that has the 6, 7, 10, 11, I could access that part by choosing the second and third row and the second and third column. If you've programmed before, usually when you're working with vectors, matrices, arrays, they're 0 indexed. In Matlab is 1 indexed. So A11 returns me the first element. It's not A00. One other cool thing that we may use later is the colon syntax can be used all by itself. It actually just creates a range. So if I did something like 1:10, it gives me back all the numbers from 1 to 10. And so say I want to assign this to a variable. Let me check the size of W. So that creates a row vector with the elements 1 to 10. It's simpler to do than typing 1 through 10 manually, right? And so just to extend this a little bit, we aren't limited to only scalars, vectors, and matrices in Matlab. You may have heard of a data structure called tensors. And so those are multi-dimensional matrices. So it's not a table, it's more like a cube or a hypercube. So you can, instead of having a 2x2 matrix, you can have a 2x2x2 tensor. So in this Matlab tutorial, we're going to go through some basic arithmetic in Matlab. We're first going to talk about the usual operations you see in programming, which are plus, minus, multiply, and divide, and also the use of parentheses. So I'm going to first create some matrices for us to use. Okay. So suppose I want to add 2 matrices. That's very simple. A plus B. If I want to subtract 2 matrices, it's A minus B. If I want to multiply 2 matrices, that's A asterisk B. So one thing to note about multiplication is this is pure matrix multiplication, which means the inner dimensions of the matrices of A and B have to match. So for example, if I create another matrix which doesn't have the same number of rows as A has columns, it's not going to work. So say, so the size of B2 is 3 by 2 and the size of A is 2 by 2. So if I try to multiply A times B2, I'm going to get an error that says inner matrix dimensions must agree. So this does mean, though, I can do this, right? So if I transpose B2, it's 2 by 3, and so a 2 by 2 matrix times a 2 by 3 matrix will give me a 2 by 3 matrix. So you can also divide matrices with a /. So, but if you remember from linear algebra, there isn't really a matrix division like that. So if you want to know what it means, you can look it up on the internet. There's a / division for matrices, and there is also a / division, which we are going to cover in a later tutorial. By the way, if you want to divide two numbers, that's very simple. We use the right slash for that. So the next thing we're going to talk about is order of operations. It's generally what you'd expect. Anything in parentheses happens first, and then multiplication and division, and then addition and subtraction. So if I have A plus B times C, I would get that. So if I did B times C and I assign it to a variable D, and I add that to A, I get the same thing. So you can confirm that the multiplication is happening first. If I wanted the addition to happen first, I would put parentheses around them. So we can confirm that what happened in the parentheses came first. So another thing you might want to do when you're implementing an algorithm or writing some code is element by element operations. So we've looked at matrix multiplication, which kind of does, if you're looking at row I, column J of the output, that actually does a dot product between row I of the first matrix and column J of the second matrix. Something we want to do often when we're coding is element by element multiplication. And so let's just look at what we have for A and B again. So that's pretty simple in Matlab. You just put a dot before the multiply sign. And so it multiplies each element by each corresponding element in the other matrix. This also works for division. So a dot slash. So if you remember from your linear algebra classes, there are some different types of multiplication that you can have when it comes to matrices and vectors. The first one we're going to talk about is the inner product. If I have x equals 1, 2, 3, y equals 4, 5, 6, and I want to do an inner product between these two vectors, one way to do that is simply by using what we already know. So x is a 1 by 3 vector and y is a 1 by 3 vector, and I want the result to be 1 by 1, which is a scalar, that means I can transpose y and multiply x by y as matrices. Right, and so that would be 1 times 4 plus 2 times 5 plus 3 times 6. Another way you can do the dot product in Matlab is by using the dot function. And so we'll cover functions more in a later lecture, but we'll introduce you to some today. So another product you might be interested in is called the outer product. And so that would be just the opposite of what I did before. So instead of transposing y and leaving x alone, I'm going to transpose x and leave y alone. So that would give me a 3 by 1 vector times a 1 by 3 vector. And so the result would be a 3 by 3 vector. Right, so that's the outer product. And there is no function for outer product in Matlab. And so one thing to note is that usually when we represent vectors, when you're reading a textbook or sitting through a lecture, the vectors are column vectors. So they have many rows but only one column. And so that's kind of the opposite of what I've done just now. And so for the inner product, you usually see x transpose times y, and then for the outer product, you'd see x times y transpose. So just the opposite, since I've been using row vectors. Lastly, there's the cross product, right? And so the cross product is the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them, and then you use the right-hand rule to determine the direction of the result. All right, so dot product or inner product is not a vector, so it doesn't have a direction, but the cross product gives you back a vector. And so that's pretty simple to do in Matlab also. It's just a function called cross. So in this tutorial, we're going to talk about Matlab functions and constants. So built-in functions and constants to be specific, and then how you can define your own functions later on. So by functions, what I mean is mathematical functions like sine, cosine, tangent, exponential, log, and square root. And so those are pretty much what you'd expect if you've ever coded in any other language before. So I can do sine of 0, gives me 0. I can do cos of 0, gives me 1. Tan of 0, of course, would be also 0. So let's look at these trigonometric functions for a little bit. So one thing is that because Matlab works on matrices, I can actually pass in more than just one number into sine. So suppose I use the matrix we had before, 1, 2, 3, 4. If I pass that to sine, what that does is it calculates the sine of every element of A and returns a matrix the same size as A. So I can do all of that separately, of course, just to show that it is indeed doing that individually for every element. And so all MATLAB functions generally work like that. Some other functions you might want to use is the exponential function. That's exp. There's the log, which is the opposite of the exponential. So if I do log of exp of 1, I should get back 1. I can do square root, sqrt. Okay, so those are some very simple elementary functions in Matlab. There are also some built-in constants into Matlab that you should know about. So for example, pi, that's just pi. So if you do something like have a variable called pi and you assign it to something else, now I cannot use the original variable pi anymore. So what I would do if I want pi back is I would go into my workspace and delete pi, right? And so now if I type pi again, it's now back to original pi. Generally, I would avoid overwriting built-in constants. So one weird thing about Matlab is it doesn't have the variable e. So if you want the variable e, you actually have to do exp of 1, which is e to the power of 1, which is e. Another important constant is I. So if I do square root of minus 1, I get 0 plus 1 times I. I can also just type in I and it would give me the same answer. So you can also do things like I times I, which should give you minus 1, or you can do I squared. So you do exponents using the hat symbol. So that also gives me minus 1. So there are also some important functions for initializing matrices that you should know about. So the first one is the I function. So you've seen I in the sense that if I have a matrix A, then A times I should equal A. And so I is the identity matrix, and it's a square matrix with ones on the diagonal and zeros everywhere else. So suppose I want to create a 3 by 3 identity matrix. I could do something like this, which would be a little bit inefficient, right? Or I could do I3, which gives me the same thing. Another thing you might want to do is create a matrix of all zeros. So that's just the function zeros. So that gives me a 3 by 3 matrix of all zeros. If I want to specify different dimensions, so I don't want it to be a square, I can pass in multiple dimensions. There's also a function called ones, which does a similar thing. It creates a matrix of all ones. You pass in the size the same way. So the next thing I want to teach you guys to do is how to define your own functions. So generally, you want to, for every function you create, you want to put it into a new file. So I'm going to go new function. So it gives me some boilerplate code that I can use. And this is good because it'll help me explain the syntax of a function to you. So when we create a function, it starts with the word function. If your function returns things, you can specify the output arguments over here. If there are more than one output argument, you can specify it as an array. If there aren't any output arguments, you can get rid of this part completely. And if there's only one output argument, you can get rid of the brackets. So let's suppose I want to define the hyperbolic sine function, which Matlab probably already has, but we're going to do it anyway. So it's going to take one input argument called x and take an output called y. So Matlab has some useful syntax highlighting. It'll give us a warning, stating input argument x is unused since we haven't written any code yet, and then it's returning a value y, but we haven't set y to anything yet. So let's save what we have so far. You can do Command S or go to File Save. So we'll save it. So one thing to note is you have to save the function name has to be the same as the file name. And so, like I mentioned before, Matlab already has its own signage. So we don't want to overwrite Matlab signage. So we're going to call our signage something else. I'm going to call it my signage. I'm going to rename this file to my signage. Alright, so now I'm not getting that warning anymore. Okay, so we're going to define our own hyperbolic sign, which is defined as the exponential of the input minus the exponential of the negative of the input, and then taking 1/2 of that. So let's do that. So inside the function, I have to set y. Remember, because I was getting a warning that y was not set. It's p of x minus p of minus x. And then remember, I want to put a semicolon here so that I don't see the output of this expression. I'm going to get rid of this comment because this function is pretty trivial, but in general, if you have a complicated function, you should probably comment it so you remember what you were doing later on, or whoever else is reading your code will understand what you're doing. And so you can write comments using the %sign to comment code. So I'm going to save that. And I'm going to use this function. So my signH, let's say 1, 0. Right, so we can see from this image that hyperbolic sign crosses 0 and then it increases as x increases. So that's what we should be seeing. Remember that Matlab works with matrices though. So if I wanted to, I can say x goes from 0 to 10 and I want to calculate the hyperbolic sign for all of those values. I can just pass in x and I'll get back hyperbolic sign for all of those values. And so that's how you define your own function. Probably yours in the future will be more complicated than that, but hopefully that was a useful, simple example. So we're going to do one more function example here. It will illustrate some new concepts. So I'm going to, instead of clicking the new button and choosing function, I'm actually going to right click on the workspace and I can see an option to create a new file and I can create a new function that way. So I'm going to call this new function isEven. Okay. And so you can see Matlab has already replaced, so before when we created a function from a new file, it called it Untitled. But now that I've given it a name to start, Matlab already knows to change the function name to that name. Okay, and I'm only going to have one output argument again, so I can get rid of these brackets. And the input argument is going to be x. And I'm going to add a comment, returns 1 if x is even. Okay, so if you've done programming before, you've probably heard of the modulo operator. Although I haven't mentioned it in this tutorial series yet, it does exist in Matlab. So in Matlab, because the percent sign is used for comments, we do not use the percent sign for modulo if you've done that in C or Java before. So instead, we use modulo by calling a function called mod. Do mod 2, 1, sorry, 2, 2, right, 3, 2. So basically it returns us the remainder. Okay, and so this should be very simple. We want to return 1 if x is even. So we know we want to mod 2. So y equals mod x 2. Okay, but we have a problem here because when you take the modulo of an even number with 2, you will get 0. But if you take an odd number modulo 2, you get 1. So that's kind of the opposite of what we want. But what we can do is we can use the tilde operator, which does a logical negation. So tilde 0 gives us 1 and tilde 1 gives us 0. So what we want is to put the tilde in front of the mod. Okay? And so now if I call is even 1, 2, 3, 4, 5, we should get 1s in the spots where the input is even, which we do. So for 2 and 4 we get 1, for 1, 3, and 5 we get 0. So in this MATLAB tutorial we're going to talk about some basic linear algebra in MATLAB. The first thing I want to talk about is how to solve linear equations. So in general, these are in the form of ax plus b, where a is a matrix, x is a vector of the variables you want to solve for, and b is a vector of constants. So if you remember from linear algebra, a system of linear equations is when you have more than one variable and the same number of linear equations. So in this example I'm looking at right here, the variables are x, y, and z, and because there are 3 of them, I have 3 different equations. So one way of writing the problem is just writing the equations out explicitly like this, or you can write it out in matrix form. So in this example, A would be 3, 2, minus 1, two minus 2, 4, minus 1, half, minus 1. Okay, so that's A. B is 1 minus 2 minus 2. Okay, so when you're working with equations like this, you might be tempted to do just simple algebra. So you could say x is equal to the inverse of A times B, because mathematically that works. So I can do that, Oh, and right, I have to make B a column matrix. So A times B. Sorry, I used the wrong B. Okay, so inverse A times B. So I get 1 minus 2 minus 2, which is the answer given on Wikipedia. So sometimes when you try to do something like this, Matlab will give you a warning. This is a very inefficient way of calculating this answer. This Matlab already contains algorithms to solve this problem. So if you remember from before, when we were talking about operations, we were talking about the division operations and how there is a / division and a / division. So this is the use case where you'd want to use the / division. And if you kind of think about it, if these were scalars, x would be b divided by a. But since they're matrices, we write the answer like this. So a / b. So it's kind of like a is underneath the b, right? And so if I do that, you can see that I get the same answer as when I did inverse of a times b. So that's how you solve systems of linear equations in Matlab. So now we're going to talk about some other linear algebra concepts that you can do in Matlab. One of them is taking the determinant of a matrix. And so that is just a simple function called det. Okay. So remember A was 3, 2, minus 1, 2 minus 2, 4, minus 1, half, minus 1 from the last example. We can also compute the eigenvalues of a matrix. So Eig A, Eig. And now you know when we compute eigenvalues, we usually want the corresponding eigenvectors. Now, so one interesting thing about Matlab that differs from other languages is that what is returned by the function is not set in stone, it's dynamic. So if we look at the documentation for the Eig function, we see that if there's one output parameter, it returns this little e. And the Matlab documentation says E contains the eigenvalues of the matrix A. But say I want the eigenvectors also. And so you can see these different function signatures. So if I assign the return values of Eig to two different variables, I can get back, let's read here, a diagonal matrix D of eigenvalues and a matrix V whose columns are the corresponding right eigenvectors. So the eigenvalues are going to be returned in a matrix called D, and the eigenvectors are going to be the columns of the matrix V. So let's try that. Equals Eig A. Right, so we get a diagonal matrix D, which has the same eigenvalues as before, and then the eigenvectors are all in V. And so let's just confirm that the definition of eigenvalues and eigenvectors holds. So A times V should equal V times D. Right, and so Here's another thing interesting about Matlab is that if we want to check if two things are equal, we can generally use the equals equals as we do in regular programming. So 1 equals equals 1 is 1, which means true. 1 equals equals 0 is false. So if we do A star V equals equals V star D, we get false, which is surprising because they should be equal given that that's the definition of eigenvalues and eigenvectors. But we have to remember that there's always in programming some round off error. So if we subtract A times V minus V times D, we should get back a very small number. Right? And so we do that, we see 1 times 10 to the minus 14, which is indeed very small. So for all intents and purposes, they are still equal, even though equals equals returns false. Now, so that brings us to the next thing I want to talk about, which is, so we have this matrix A times V minus V times D, which kind of represents all the differences in those two matrices. And so we want to ensure that all the values are small. Now there are 9 different values in this matrix, so it's kind of hard to tell how big or small it is collectively. So one thing we want to do sometimes when we have vectors or matrices is we want to calculate the distance from the origin. And so we can do that with vectors. With matrices, we call that the norm. And so typically, all the elements, so in a Euclidean space, for example, it's all the elements squared, added together, and then you take the square root. So in Matlab, there's a function called norm that does this. So let's just see what that gives us. So it gives us one very small number, so 5 times 10 to the minus 15, which we again can use to confirm that it's very close to 0. So A times V is very close to equal to V times D. And if you remember from your math courses, there are different kinds of norms. So I talked about the Euclidean norm, which is a norm 2. We can actually do a p-norm, which is, so instead of taking the square and summing them all together and taking the square root, we do every element to the power of p, sum them all together, and take the pth root. So, and that's just the second argument of norm. So if I put a 2 there, I should get the same answer because p equals 2 by default. So you can't use p equals 3. You can only use p equals 1, 2, infinity, or fro. And so 1 would be the Manhattan distance. So in this lecture, we're going to talk about for loops, while loops, and if and else statements in Matlab. The first thing I'm going to talk about is the basic syntax of a for loop. So the basic syntax of a for loop is for index equals some array of numbers, so it can be anything. So for argument's sake, I'm going to use just a bunch of random numbers, and then I'm just going to display them to the output. Okay? So all that does is it sets I to the first number for the first iteration, it sets I to the second number for the second iteration, and so on. We've seen before that Matlab can create ranges with the colon though, which is probably a more common use of the for loop. So you want to count from 1 to 1,000 or 1 to 10, And so the way you would do that is for I equals 1:10, which actually in Matlab is generating the array 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm just going to display I again. And you can see that it goes through every value of I. So now that we have the basic for loop syntax in Matlab, what I want to do is go through a little more complicated example. You've heard of a concept called the mean squared error. If you haven't, I'll show it to you on Google. So the mean squared error is if you're trying to predict something, you're going to have some error for all the data points between the true values and the predicted values. And so the mean squared error basically takes the difference between your prediction and the actual value, squares them all, sums them together, and divides it by the number of points. And so you can see how we might be able to use for loops to implement that. So now, since we don't have any data or any error, we're just going to pretend that we do. So I'm going to use the rand_n function to create an array of size 1000 by 1. These error points are going to be normally distributed, which is often an assumption that we make anyway with statistical models. Okay, so now I have a 1000 length array of errors, which represents the difference, so I don't have to calculate the difference in this equation. And so now we can go ahead and calculate the error. So the first thing we want is the sum of squared error, right? So that's just the sum of all the individual elements. So I can do that by first initializing the sum of squared error to 0. And I'm going to do a for loop from 1 to 1000. And I'm going to accumulate the sum of squared error being the square of each individual error. Okay. And so now that I have the sum of squared error, I'm going to divide that by 1000 to give me the mean squared error. So one thing to note about Matlab is that for loops, while loops, and if statements are actually very inefficient. So you don't want to use them unless you absolutely have to. And so I want to demonstrate how that is the case. So we have this mean squared error example. I've pre-written the code, and I use a statement called tick and talk to time how long it takes. So you basically, you start your code with tick, you put all your actual code after that, and then you put a talk at the end, and then it will tell you the elapsed time it took to run that code. So I've already pre-written it, so I'm going to paste it out here. Tick, T-I-C, talk, T-O-C. Okay, so that took 0.005668 seconds. Okay, now if we look again carefully at the mean squared error, we notice that we want to square each element and then sum them all together. And so that sounds a lot like the dot product, right? So if you take the dot product of a vector with itself, you're just squaring each element and then summing them all together. So if I wanted to do the mean squared error equation in a more compact way, what I might want to do is the dot product between E and itself, which is E transpose times E as a matrix, and then divided by 1,000. Right, and so that gives us the same answer as before. And so if I put a tick and a talk around that, I get 0.002896 seconds. So it's significantly faster than using a for loop. Okay, so that's for loops. Now we're going to talk about if statements. So what I want to do is I want to revisit the is even problem that we talked about in an earlier tutorial. So if you recall, what I did was I created a function that returns 1 for all the entries of x that are even and returns 0 otherwise. So you could do this with if statements. Let's say x is just 1 to 10. All right, and we want to say y is initialized to an array of zeros. And we'll do for I equals 1 to 10 if mod x of I and 2 is equal to 0, then x is even, right? So that means we're going to set y of I to 1. Else y of I is 0. So we don't really need that else since y of I is already 0, but I'm including it so you know what an else looks like. Okay, so now if we look at y, it has the 1s where we expect it, which is where x is even. Okay, so now let's do a similar example, also using for loops and if statements. So the problem is, let's say I want to sum all the elements of an array that are divisible by 3. So let's just use the same x as before. Let's reinitialize y to all zeros. Or sorry, we don't even need to do that. Let's set some sum equals to 0. And so now I'm going to loop through all x's again. For I equals 1 to 10. So if mod xi, so now we're going to say 3, right? So if it's divisible by 3, we want to sum that element. Okay, sum equals sum plus x of I. And now this time we're not going to include the else. Okay, so s is 18, which is equal to 3 plus 6 plus 9, which we expect. So that's the correct answer. Now, of course, there's another way to do this. So if you only want to look at the elements in x, so notice how whenever we use I, we're actually saying x of I. We can just do this. For little x equals big X, right? Because the little x is going to just go through every element in the big X. We're going to start again, so we're going to reinitialize s to 0. Say for x, little x equals big X. If mod little x 3 equals 0, sum equals sum plus little x. So if we look at sum again, we still get 18. So now let's look at another problem. So suppose we want to find an element within a matrix. So suppose again we have the same x, and I want to find the number 8. So I can use a while loop for that, right? So I can say, I can set a variable called found equals 0, meaning false, and then I can say while not found. So I'm going to initialize an index x for x. I'm going to say while not found I equals I plus 1 if x of I is equal to 8, which is the thing I'm looking for. Display I found it. Okay, so I made a little mistake there. We went out of bounds because I went to 11 and the size of x is only 10. So what we did was we forgot to set found to true after we found x of I equals 8. So I'm going to reset this code. I equals I plus 1 if x of I equals 8. Display I found it. Set found to true. And now end the if statement. Right, so now we go up to 8, print out I found it, and then we quit the while loop. So while loops only go until the condition after the while is false. So it'll continue to go while it's true, and then when it's false, it will stop. Another way we could do this, though, is we could, again, use a for loop. So generally speaking, whenever you can use a while loop, you can also use a for loop. It's just the syntax that will change and a little bit of the structure of the code. Suppose I want to look through all of x again. So I want to say if x of I is equal to 8, display I found it. So now this works, but there's a problem, right? Because in the original while loop, we would only go up to 8 and then we would quit, versus this for loop goes from 1 to 10, so that's inefficient because it's doing extra steps. So what we can do to avoid that is use the break statement. So just to prove to you that it works, I'm going to print out for I equals 1 to 10, f. So again, if x of I equals 8, display I found it, break, end. So now you see I only goes up to 8, it finds 8, it breaks, and then it doesn't go to 9 and 10. In this Matlab tutorial, we're going to be talking about different kinds of data types. So things that are not what we've seen so far, i.e. numbers, scalars, vectors, and matrices. So one thing that we've been implicitly looking at are strings. So whenever I display something like this and I put it into single quotes, the thing that is inside it is a string. Later on, when we look at opening files, we'll specify the file names as strings. So a string is basically any sequence of characters. So we've seen the workspace, but there's also a function called whos that lets us look at all the variables in the workspace and see some stuff about it. So you'll notice a column called class. So far everything I've created is a double, so we have no actual strings yet. If I use the class function and I look at an actual string, let's just use the IFoundIt string again, you'll see that it returns car. So if I set a variable called myString equals IFoundIt and I type whos, you're going to see now that there's a variable with the name myString, size 1 by 11, so strings are considered row vectors, and it's of type car. So the next topic we're going to talk about is structs. We've seen so far in Matlab numbers, matrices, vectors, arrays, strings, but that doesn't leave a lot of flexibility compared to other programming languages. So if you're familiar with Python, maybe you've seen the dictionary data type, or if you've used Java, it would be the hash map. Or if you've coded in JavaScript, you may have used JSON. If you've ever used any of those before, you know that those data types are very flexible because a JSON can store other JSONs, it can store arrays, whereas in Matlab we've so far been constricted to only numbers. So in Matlab, when you want to declare a struct, it's very easy. So we call our struct myStruct dot name equals myNewStruct. Okay, so this creates a struct with one field, which is referred to as name, and the value is myNewStruct. If I do class on myStruct, it tells me that it's a struct. So the cool thing is you can add new values to the struct dynamically. So I can say myStruct.age equals 25. So now myStruct contains two fields, name and age, and notice that they are different types. So if I do class myStruct name, it's a car, but if I do class myStruct age, it's a double. So there are also some useful functions that act on structs. myStruct name. So isField will tell you if a field exists within a struct. So I just checked if the field name was part of myStruct, and it returned 1 because it is. Let's try gender. So that returns false because gender is not a field in myStruct. There's a method called rmField. So if I want to remove a field from a struct, I spelled it wrong. Okay. So now myStruct only contains the field name because I removed the age field. There's a function called setField. So you might want to use this if, for example, the name or the value is set dynamically while the program is running. So you can't do mystruct dot something. You have to set the field some other way. And I spelled field wrong again. So now you can see I've added a field called gender with the value F. So the other thing I talked about is that a struct can actually contain a struct. So suppose I want to add a new field to my struct called contact, and I want to give a phone number to my contact. 2, 3, 4, 5, 6, 7, 8, 9, 0. So I've set the phone number on this struct, and so you can see when the struct prints out now, the contact field is just a struct, but it doesn't print what's inside. And so now, since contact is a struct, I can set other fields as well. Okay. So my struct now contains the contact field as a struct, and contact is also a struct. So the last thing about structs that I want to mention is an alternative way to initialize a struct. So far we've been manually entering each struct value one at a time, but you could also do something like this. Name Bob, email bob@gmail.com. Right, and so what that does is it takes in an arbitrarily long list of parameters where the first parameter is a field, the second parameter is a value, the third parameter is a field, the fourth parameter is a value, and so on. So the last data type that I want to talk about today is the cell. So the cell is very similar to a struct in that it contains arbitrary fields. The difference is you might see a cell as more of like an array that can hold indices other than just numbers, versus you might see a struct as more of an object that contains information about some type of thing, and then a cell might be, like an array of those things. So the cell syntax is very similar to the Matlab matrix and array syntax. Okay, so to initialize our cell, we're going to use curly braces. We're going to set the field 1. Doesn't have to be an integer. We're going to set it to the value hello world. Okay. So now if I print out my cell, simply contains hello world. Okay, so now I'm going to set another field. I'm just going to call it A, and it's going to be a matrix. Okay. So now I have 2 keys and 2 values for my cell. I have the key 1 and the key A, and then the values hello world, and then this 2x2 matrix. So what I can usually do with Matlab variables is just type it into the command window and see what it prints out. You can see that it has printed out a lot of stuff. So you generally won't want to do that, but notice how now I can access key 1 and it returns hello world, and I can access the key A and it returns the 2x2 matrix that I previously stored. So this is good for when you want to store things by name, for example, instead of trying to put it into an array. And you can also store heterogeneous information, so different types. So today we're going to learn about how to make plots in Matlab. So one of the very simplest plots you can make is just to plot a series of data. So one very popular series is the Fibonacci sequence. And that's just adding the two previous numbers to make the current number. Right, so here are the first 8 values of Fibonacci. And so to plot a sequence, all I need to do is call a function called plot and pass in the variable. Right, and so that's Fibonacci. Now notice how the x values have been set automatically. So it starts at 1 and increases sequentially. So the next thing we can do to make it a little more complex is to have actual values for x. So suppose I want x to increase by 0.1 every time. So I might do 0, 0.1, 0.2, 0.3, 0.4, 5, 0.6, 0.7. Right. So now I have an x and y, which is what you're probably more used to when you're creating a two-dimensional plot. And to plot x and y, you just pass in x and then y into the plot function. Right, and so now you can see the y-axis is the same as before, but the x-axis is now no longer 1 to 8, it's 0 to 0.7. Notice that the size of both x and y have to be equal. Right, so if I do this, this is not going to work, right? All right, so the next thing we're going to do is something a little bit more complex. We're going to plot a function. So the first thing we need to learn about is a function called linspace. Linspace, what that does is it creates the range of values of x for us. So we just pass in where we want it to start, okay, where we want it to end, and how many points in between. So I'm saying x is going to go from 0 to 100 and has 200 points in between. Now to calculate y, all I have to do is sine x. We're plotting the sine function. And so in Matlab, functions generally apply element-wise, right? So every value of x, you call sine x, and then it assigns the value of that sine x into y. So I'm going to plot x and y again. And so now I see sine x going from 0 to 100. So one thing you might notice about this is the lines are pretty jagged, right? It's not a smooth graph, but you know that sine x is actually a smooth graph. So the reason why that is if we look at x again, let's look at the values. Remember, there are 200 points for about a range of 100. And so that's a very low resolution. The last value here is 100. The second last value is about 99.5. So there's only about 0.5 distance for every unit of x. So to give us better granularity, we might want to reduce the range first of all, and then put more points in between. So let's recreate x. Let's say it's going to go from 0 to 2 pi and have 100 points in between. Right, and so y is going to be exactly the same. We're going to plot x, y again. Right, and so now you can see that it's a lot more smooth. So adding to the complexity of this a little bit, suppose I want to plot two functions on the same plot. And that might be useful if you want to compare two different series. So let's say the second function we want to plot is cosine of x. Just say y2 equals cos x. And so if we type in just plot, we can see some different function signatures for plot. If you look at the third one, it shows us x1, y1, ... xn, yn. So what that's telling us is that for every pair x and y that we want to plot, we just pass them in adjacent to each other. So in our case, we're going to have x and y, and since it's the same x for both y and y2, we're going to just pass in x again, say y2 over there. Alright, and so now you can see both sine x, which is the blue line, and cos x, which is the green line, on the same plot. And Matlab automatically changes the colors for us so we can differentiate between them. One thing you can do if you want to make it a little more fancy is you can specify a line style. And so those are also passed in adjacent to the x and y's. Right, and so now it's even easier to differentiate between the two lines. So the second chart, cos x, is a bunch of dots. And I made a mistake because the dash is the default. That just makes a regular line. If you put in two dashes, it makes them into dashes that you can differentiate between like that. Okay, so now let's say I want to save this plot to my hard drive, or maybe put it on the internet or a document. So you go to File, Save As. So you see the default file format here is .fig, and that is a Matlab file, so only Matlab can read those files. There are some other types of formats here that we can look at, such as PDF. If you want to save it to a PDF and then print it out later, you can save a PNG or a JPEG. So if you want to put it in a Word document, or you're writing a paper, or you want to put it on your blog post, you might want to use JPEG or PNG. And so I'm going to use .fig, since you probably already know what a PNG and a JPEG look like. Alright, so I already made a test.fig. I overwrote it. So now that I have it, so you can see right here, saved into my current working directory. If I want to open an existing figure, I do that through a function called openFig. I pass in the file name, and it opens back up the figure. And so the nice thing about MATLAB figures is that I can still zoom in, right? I wouldn't be able to do that really with a JPEG. It would look very blurry. Of course, I can zoom out. I can use the hand to move around the chart. Right, so it opens back up the same figure I had before, so I can play with it. As if I had made it for the first time. So in this tutorial, we're going to be talking about different types of plots that could be useful for data analysis. So the first type of plot, if you've ever used Excel or watched a PowerPoint presentation, you've probably seen this. You've probably seen most of these actually. So the bar plot. So suppose we have some sequence of data. Let's just say x equals 1 to 10. And we want to plot this on a bar chart. We just call the method bar, pass in x, and we see the bar chart. So this does pretty much the exact same thing as the plot function, except instead of connecting them all in a line, it connects, well, it doesn't connect the points at all. It gives them each their own individual bar. So just for reference, let's do our sine example again. Okay, so we're going to do bar xy. Right, so this is a bar chart of the sine function. Okay, so the next type of plot that I want to talk about is the histogram. So if you've ever studied probability, you know about probability distributions, and given a data set, we might want to figure out what kind of distribution does it follow. So let's generate some data where we know the distribution. So I'm going to create 1,000 points that are normally distributed. So if I plot this, it doesn't do much. It just looks like noise. So I won't be able to see much from that. What you want to do is you want to call a function called hist, which will automatically create a histogram out of your data. So I'm going to call the simplest version, which is hist of just the data. Right? And so you see that it's pretty much normally distributed. There's a little bit more weight on the right bar than the left bar in the center. And so the resolution for this chart is not that great. So what you can do is you can set the number of bins, right? So if you have a lot of data, in our case 1,000 points, you can set the bins to maybe say 50, okay? And so this gives us a much more granular representation of the data. So now we can see it still looks normal. You know, there's a little less data than expected, kind of right here at 0, and then a little more to the right of that. But generally speaking, this plot is pretty much what we'd expect. The next type of plot that I want to talk about, again, if you've used Excel, you've probably seen this, or PowerPoint, is a pie chart. So we're going to work with some simple data again. Let's say x is 1 to 5, and all I do is I call a function called pi, pass in the data, right? And so it automatically splits up the data. So the dark blue is the first element, light blue is the second element, green is the third element, and so on. And so there are ways that you can label this to make your visualization better, and so when you show it to people, they know what everything stands for. So there's a lot of documentation on the Matlab website for that. The last type of plot that I want to talk about, probably the most useful for data analysis, is called the scatter plot. So we're going to again return to our sine example. So x is linspace from 0 to 2 pi. Let's give it 1,000 points. So now I'm going to do something a little different. I'm going to set it y equals 10 times sine x, so that the sine x has an amplitude of 10, and then I'm going to add some random noise with variance 1 centered at 0. And so the reason why I want to scale it by 10 is so that the sine wave is big compared to the noise. Otherwise the noise will just take over the shape of the sine wave. I did that wrong. Okay. So now if I were to just plot x and y, so you can see a noisy sine wave, which is okay. If I do it in a scatter plot, I can see that pattern pretty much just as well. So the nice thing about our sine x example was that the data was ordered. Now suppose that my data is not ordered. So instead of having linspace, my x is just a bunch of random points. So x is normally distributed with standard deviation of 2. Okay, and so y is going to be, let's say, 5 times sine x plus some noise. Okay, so if I plot x and y now, I don't really see anything. It just looks like a bunch of craziness. But scattering, so a scatter plot, that will just plot all the dots, so all the individual data points, right? And so I can now very clearly see the sine wave that I'm supposed to see. So if you're doing data analysis, your points are not ordered, you want to use a scatter plot. So in this tutorial, I'm going to talk about loading and saving data. So a lot of the time when you're doing data analysis, your data is going to be passed around in files that you might download off the internet or stored on your hard drive or something like that. So you're not going to be manually typing in matrices into Matlab all the time. The first thing I want to talk about, since it's probably going to be really popular with Windows users, is Excel. So Excel uses a format called .xlsx, and there are two functions in Matlab that are useful for reading and writing XLS files. Okay, so if you type in help XLS read, you can see the documentation for the XLS read function. There's also a function called XLS write that you may want to look into. So the reason I'm not going to cover XLS read and write in this tutorial is because, first of all, it's not perfect. So I'm on a Mac, so I used Google Sheets to export an XLS document. And it's a very simple document. It's just a 3x3 matrix with the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9 in Matlab. So XLS read Matlab example gives me an error when I'm trying to read this file. So we're not going to be working with XLS. In addition to that, so if you've ever participated in a Kaggle contest or you get a file to work with from school, I've never seen anyone ever use XLS. Usually it's a CSV. Sometimes it's a .mat file, which is a Matlab file. So we're going to be working with those. So CSV, I would say, is the most common. It stands for comma separated values. So your file will look something like this: 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I'm going to save this. CSV example.csv. So we have a function called CSV read, CSV example. Okay, and so that did exactly what I wanted it to do. So you can see how the CSV file pretty much one-to-one corresponds with the matrix that you would get after you read the file. Now, let's say I have a new matrix. Let's create something a little different. Okay, so just 5s along the diagonal. I'm going to call CSV write be another .csv. So I did it backwards because I didn't know. So I'm going to write the matrix B to a file called another.csv. So if I look at this file, alright, so when I double click it, Matlab gives me kind of a CSV editor. So now what I've done is I've opened the same file in a text editor on the command line console, and so you can see again what we'd pretty much expect, a CSV of the matrix that we made. So that's the nice thing about CSVs, is they don't just work with Matlab, they work with many other types of programs. It's just a plain text file. So now the other way that we can read and write files is the .mat file, which is Matlab specific. So I'm going to clear my workspace, and you'll see why. I'm going to create one matrix A, 1, 2, 3, 4. Oops. I'm going to create another matrix 5, 6, 7, 8. Okay, so now I have two matrices, A and B. So now what Matlab lets you do is it allows you to save your entire workspace all into one file. And so all I do is I call save my workspace.mat. Okay. So now if I look at this file, So I open this .mat file in a text editor. Notice how it just shows me a bunch of garbage. So this is binary data specifically for Matlab. So that's why you might prefer to use CSV, so you can be cross-platform or cross-program. Okay, so I'm going to clear my workspace again, and I'm going to call load my workspace.mat. And so what load does is it just reloads your entire workspace that you saved into the .mat file. And so that could be useful if you don't want to save every variable individually into their own CSV. What you can do is if you don't want to save all the variables, you can pick specific ones. So let's say I create another matrix C, 9, 10, 11, 12. Okay, so I have variables A, B, and C, but I only want to save A and C. So I'm going to give it a file name, ac.mat. I'm going to pass in, so you can't pass in the variable, you have to pass in the name of the variable. So I'm going to pass in A and C. I'm going to save it. I'm going to clear my workspace. And so now when I load ac.mat, it just gives me back A and C only, but not B. So in this lecture, we are going to talk about more plotting. We're going to talk about subplots, so that's putting more than one plot into the same figure. We're going to talk about three-dimensional plots, and we're going to talk about how to label plots. So you want some field for the x-axis, the y-axis, and the title. So let's go into subplots. So suppose I have some function of x, so let's just say sine x. Then I have another function which is just sine x plus some noise. Okay, so I can plot these individually, or I can plot them together. Or I might want to stack them up or something to see if there's a correlation between them. So the way we do that is with subplot. So we call a function called subplot, and it takes in three values. Okay, so the three values are the number of rows in the subplot, the number of columns in the subplot, and then which subplot you're about to plot. So since I have two subplots, let's say I want 2 rows and 1 column, and I want to set the first plot. So I just call subplot 211, and I say plot xy. Okay. So now my figure has xy in the first row and first column. Okay, so now I do subplot 2, 1, 2, okay, because I still have 2 rows and 1 column, but now I want to plot something in the second slot. And here I'm going to plot x and z. So now if I look at my plot, right, so you can see the two plots stacked up on top of each other, instead of overlaid. So the next thing we're going to talk about is 3D plots. So suppose we have some two-dimensional data set. I'm just going to make it random noise. Okay, so if we look at the matrix Z, we see that it's 100 by 100. So the rows you can think of as the x-axis, the columns as the y-axis, and then the value as the third dimension. So how would we plot this? And so there are a couple ways you may have seen already from your math courses. So we can plot an actual 3D plot. So sort of how you draw a cube on a two-dimensional piece of paper, or you could use what's called a contour plot, which draws lines where the value of the function is equal. So we're going to do both of those. The first one is a function called surf. So you pass in the matrix, and so you can see the x-axis and the y-axis both go from 0 to 100. If you look up the documentation, you can set the x-axis and the y-axis manually, and then the height is the value of the function. So what I did just now is I clicked on this thing that sort of looks like a circular arrow. And so what that allows me to do is it allows me to rotate the surface plot. So now I can look at it from different angles, which could be very useful if you're doing data analysis. The other type of plot that we talked about is the contour plot. So the simplest way to call that is with the one argument, and that generates just a 2D visualization of your data. You know, the red is the really high values and the blue is the really low values. So the third thing we're going to talk about today is how to label plots. So far we've only seen plain visualizations. So let's go and plot the sine function again. Alright, so I want to give this plot a title. All I do is use the title function, a plot of sine x. Okay, so now if I look at my plot, you can see it now has the title a plot of sine x. Now I want to label the x-axis. So I'm going to label it with a very unoriginal label. Okay. So now you can see the x-axis is labeled. And you can do a similar thing for the y label as well. Okay. So that's pretty much it for labeling. Suppose I want to label a subplot. Okay, so now I'm going to create another function. I'm going to subplot 2, 1, 1, plot xy, title sine x. Okay, so once I do that, the first subplot gets the title sin x. Now I call subplot 2, 1, 2. I plot x and z, and I call title again. So it's the same function, but it's stateful. So it knows that I called subplot earlier and that it corresponds now to the second plot. Okay, so I call title again, and now my second plot has the title cos x, and my first plot has the title sin x. In this tutorial, we're going to talk about sound processing in Matlab. For this tutorial, there are no toolboxes needed. So the first thing we're going to talk about is what sound is. So sound, as you may have heard, is a wave. And it's a wave of air particles. And so when you think of a wave, usually we think of something like this, like a sine wave. We call that a transverse wave. When we think of sound, though, it's a variation in pressure, right, that bounces off your eardrums. So a wave like this doesn't really make a lot of sense. There's another kind of wave called a longitudinal wave. And this is the kind of wave that includes sound. So if we look at this visualization of a spring, this describes what is happening to air as sound travels through it. Now, interestingly enough, when you record sound on a microphone and convert it into an electrical signal, that signal can be viewed as a wave like this. So we again get a transverse wave. And so when we look at sound in Matlab, we're going to be looking at a transverse wave, even though in reality it's a longitudinal wave. So one thing you have to remember is that an electrical signal is an analog wave. And when we represent things in matrices on computers, those are digital signals. So, for example, you could have a sound recording of, say, 2 seconds long. And then that translates into a matrix of length 1000. So that would mean you have 500 samples per second. And so this process of sampling is what we call discretization. And so sampling is the discretization of data points along the x-axis, or in this case, time. The other kind of discretization we have is along the y-axis. So this is because numbers in Matlab, numbers in any programming language, can only take on certain values. So you can't have an infinitely precise number. This is because numbers are stored in quantities of, say, 32-bit or 64-bit. And so we have to not only discretize the signal in time along the x-axis, but we also have to quantize the signal on the y-axis. And so both of these lead to some error, but in general, say you're playing a WAV file or you're playing an MP3, you don't really notice these differences. They're imperceptible to the human ear. So now that we've covered a little bit of the theory behind what sound is and how it's translated into a digital signal that we can read in Matlab, we're going to go ahead and open a sound file in Matlab. But before I do that, I'm going to show you how I created the sound file. So there's a free program on all major platforms, Linux, Windows, and Mac, called Audacity. It's free and open source. You can download it just by searching on Google. And so if you have a microphone connected to your computer, you can record things. So I've recorded myself saying, "Hello world." Hello world. And I've saved it to a WAV file. I have this WAV file in my workspace. And so there used to be a function in Matlab called wave read that you could use to extract the data from a WAV file. Now notice I get a warning when I use wave read. When you search on Google for how to open a sound file, this is the thing that's going to come up. So you're going to get this warning and wonder what's going on. And so wave read is going to be deprecated, and there's a method called audio read that's going to be used instead, but this is currently not showing up in Google results. So let's look at wave read first. So it only reads WAV files. And so if you don't know, a WAV file is just raw digital sound data. So we sample the sound and we quantize it, and then we save each of those data points as an array, essentially, into the file. So there are different method signatures that we can use with wave read. We can get just the data, which I've done, or we can get the data and the sampling rate. So commonly we use fs to refer to the sampling rate. The F stands for frequency, S stands for sampling, so the sampling frequency. Now there are some interesting things we can do once we have the data. So I can plot the data. Sure, where it went. There we go. So you can see here, it pretty much looks the same as what I had in Audacity. And also check out the size of the matrix. So there are 84,480 samples just for that maybe 1 second of data. And notice that the other dimension here is 2. If you think about why that is, let's go back to Audacity. There are 2 channels. So I was recording in stereo, right? So there's the left side and the right side. So that's why there are 2 dimensions to this matrix. Now another interesting thing you can do is play sound. So I can actually play this file back. But for that I need to, so there's a method called sound in Matlab that you can use to play sound, but we need to use a different method signature for wave read. In particular, we need to get the sampling rate. So I'm going to use wave read hello world and return both the data and the sampling rate. So I do sound, pass in the data and pass in the sampling rate, hello world, and it plays back the sound. So now you might be wondering what will happen if I try to read an MP3 file. So I'm going to save this as an MP3, the exact same file. So keep in mind that wave read, of course, only works with wave files. If we want to read MP3s or any other kind of compressed sound file, you should use audio read, the new function for reading audio in Matlab, which can also read waves, by the way. Okay. So now let's say I want to play this. Hello world. And so it sounds exactly the same. So in this Matlab video, we're going to do some exercises related to sound processing. So the first exercise we're going to do is try and reverse the audio file. Please pause this video and see if you can figure out how to do it yourself first. Okay. So if you search on Google how to reverse a signal, you see two functions that pop up. There's flip LR and flip UD. So now if we look at the sound file that we opened earlier, Hello World, from the last lecture, we see that it's about 85,000 by 2. So this tells us that the samples are along the rows, and each column is the left and right channel. Therefore, we'll want to use flip UD, not flip LR, because if you flip LR, it's just going to reverse the two channels, but if you flip UD, it's going to reverse the signal. So let's do that. So you see the shape is the same. If I plot D2, it's not apparently obvious, but this is the reverse of the signal that we had before. So now I want you to play this signal. Okay, so I want to play this signal for you guys, but I have to save it first so that I can put it into the video editor that I'm using. I'm going to skip ahead a little bit and talk about the function audio write. So this is analogous to audio read. You pass in the data and then you pass in the sampling rate. Okay, so Matlab does not support MP3 in audio write for some reason, even though you can read MP3s. Let's try MP4. Okay. So now I'm going to read this file. Wait, I'm gonna get the sampling rate also. I'm gonna play this back. Or will So that was Hello World backwards. So the next thing I want to do is I want to speed up the sound wave so it plays twice as fast. I'm going to give you guys a minute to think about that. And so please pause this video and then come back once you think you figured it out. Okay, so The process of speeding up a sound wave is called downsampling. So we're going to use a integer number like 2 so that it's a little bit easier. So conceptually, what you want to do is you basically want to drop every other sample of the original signal. There are some other algorithms and functions you could apply that theoretically might give you a better sound, but just to take every other sample is the simplest way. And so if you searched for this earlier, there is a method called downsample in Matlab. Okay. And so notice that if we check the size of D4, the signal is half the length it was before because we took every other sample. And now I want you to play this back with the original sampling rate.
Hello world.
And so now it sounds like a chipmunk because it's going twice as fast and the pitch has increased. So if you think about a sine wave that doubles its frequency, that's the exact same thing that's happening here. And now the next exercise I want you to do is theoretically maybe a little bit more complicated, but I think you guys can get it. So now that I have this downsampled version of Hello World that's playing every other sample of the original, how do I get it to play at the original speed so that it's not high-pitched? I'm going to give you guys a minute to think about that, so please pause this video and then come back once you think you figured it out. Okay, so the solution to this, what we want to do is we want to play at half the sampling rate. Hello world. And so this sounds pretty much like the original. You probably can't tell that there's some information loss. This has to do with a thing called compression. So if you ever study multimedia and you look into this field further, you would learn more about that. So in this tutorial, we're going to go a little bit deeper and more general than just sound. We're going to talk about signal processing. So one of the most important concepts in signal processing is the Fourier transform. If you've never heard of this, you can go to wolfram.com and look up the Fourier transform. So if you've never taken calculus or some sort of advanced university math, this probably won't make a lot of sense to you, but if that were the case, you probably wouldn't be doing this course in the first place. The Fourier transform is essentially in more of a conceptual way. It lets you view the frequency components of a signal. So you convert a signal from the time domain into the frequency domain, and then you can use the reverse Fourier transform to go from the frequency domain back to the time domain. So now if you look at these equations, you'll notice that f of x, the original signal, is a continuous function of x. And so we call this the continuous Fourier transform. Now since we're working in Matlab and we're working with arrays and matrices, that won't really work for us. So we need a sort of discrete version of the Fourier transform. And appropriately, it's called the discrete Fourier transform. So let's look that up. Okay, so we've sampled f of x, or sometimes we call it f of t, since, if we're looking at a sound signal, it's varying in time. So we sample f of t at a certain frequency delta, so that's the sampling period. And then we assign those values at each sample to f of k, and so f of k becomes a discrete signal. One thing to note from last time is that we talked about sampling and quantization, so this is sampling only, not quantization. So once we have f of k, we can then calculate the discrete Fourier transform f of n. So this brings us to the next concept, is what's the function in Matlab that actually calculates the discrete Fourier transform? So there's an algorithm called the fast Fourier transform. Also known as FFT for short. It calculates the discrete Fourier transform in n log n time. So if you ever studied algorithms, you know about O of n, big O notation. So if you were to calculate the Fourier transform naively, you would get an O of n squared algorithm, which is slower than n log n. We don't need to worry about the details of the algorithm, just that Matlab has a function called FFT. So as an example, let's do a sine wave. So let's calculate the FFT of the sine wave. So now let's try to plot the FFT, or the transform signal. And so you'll notice it looks kind of weird. This is not what we want to see. So this is just an intermediate step that I'm showing you. So if we go back to the definition of the Fourier transform, so let's look at the discrete Fourier transform. You'll see that it's the original signal f of k times e to the power of negative 2 pi I n k over big N. So the exponent to the power of I, where I squared is negative 1, is going to give you a complex number. So there's going to be a real part and an imaginary part. You can use Euler's equation to see this more easily. Cos theta plus I times sine theta. So there's a real part and an imaginary part. So if we look back at big Y, which is the transform signal, you'll see that each of the parts here has a real part and an imaginary part. So typically when we're plotting the FFT, we usually just look at the real part. So there's a method called real in Matlab. So suppose I have some number 2 plus 3 times I. Real will just drop the imaginary part. So now I'm going to plot real times big Y, which is the FFT of little y. Okay, and you can see that there are two spikes, one on the left and one on the right. So when you're looking at the frequency domain, the Fourier transform, you really only need to pay attention to the left half. So this area is the lowest frequency. This area in the middle is the highest frequency. And because if you look at the Fourier transform again, there's this 2 pi in the exponent, and also that it's a complex number which then resolves to cosines and sines. The Fourier transform is actually periodic. So it's periodic in 2 pi. And so when we look at the continuous Fourier transform, you'll see that the signal actually repeats every 2 pi. So when you look at a signal, so let's just see if we can find one. Okay, this is a good picture of what I'm trying to explain. So usually the way that the Fourier transform is visualized is that it's symmetric around the center. So we only show from negative pi to 2 pi in the frequency domain. And then anything you see on the left side of the 0 point here is just carried over to the far right when you're looking at the discrete Fourier transform. Another thing to notice is that the transform signal is the same size as the original. So size big Y is the same as size little y. So the important thing I want you to grab from this is that the sine wave has only one frequency. Right, and so that's what we're seeing here. That's what this spike is. Now, so when we look at real signals, so we're going to look at some voices soon, what we're going to see is there are going to be multiple frequency components. Right, so when you speak or when you play an instrument, they produce different sounds because they have different frequencies playing at the same time. So we're going to go back to the Hello World from the first and second lecture. Equals audio read, Hello World, 3. All right, so remember that D has 2 channels. So we're just going to look at the left or first channel in the FFT lectures. So I'll say big D is equal to f of t of little d. So I'm going to select all the rows and then the first column. Now I'm going to plot the real part of the f of t of d. All right, so you can see the multiple frequency components that show up. This is my voice. So I've downloaded a female version of Hello. I couldn't find Hello World, so she just says hello. I'm going to read that in. So I'm going to play it just so you know what it sounds like. to do this.
Hello?
Okay, so the female voice is more high-pitched than the male voice, and so mine is a male voice. So what we should see then, I'm going to take the FFT of the female voice, and I'm going to plot that. So this doesn't tell us much because it's just a plot by itself. So we're going to use some of the things we learned before. Okay, I'm going to use subplot. I could try to plot these on the same plot, but we have a problem, right? So if we look at the size of D, it's about 85K, and if we look at the size of F, it's only 8,000, so it's a much shorter hello. And so the problem with that is if we plot them both on the same axis, one's going to be really short and the other one's going to be really long, so you can't really compare the frequencies that well. So what we're going to do is we're going to use subplot. I'm going to plot the female version up on top, and I'm going to plot the male version, which is me, at the bottom. Okay, so remember that the signal is symmetric, right? So I only have to pay attention to one side. And they're relatively the same length on these plots. So now notice that the female voice takes up higher frequencies, and my male voice takes up lower frequencies, and it's loudest on a very low frequency. So the Fourier transform can be used to analyze sound signals or any kind of signal that you want to know the frequencies of. So in this Matlab tutorial, we're going to extend what we learned last time about the Fourier transform. So last time we took the Fourier transform of a sine wave. And if you've ever studied the Fourier transform in school, you know that when you take the Fourier transform of a sine wave, you should see a delta function or a spike in the frequency domain. And what we were seeing was something a little strange. So let's suppose I set my x to linspace 0 going to 5 pi with 1,000 points. And then I plot real FFT sine of x. Okay, so what we see here is actually two spikes, not one spike. And this is due to artifacts, due to sampling. We don't have an infinite sine wave, which is assumed when we calculate the FFT of the sine wave, and then we get a delta function in the frequency domain. So what we could do, right, if you want to have closer to an infinite sine wave, you could do 0 to 10 pi. So that's 5 full sine waves, and then do 500 samples. So let's plot sine of x again. And so now you can see something much nicer. So now I want to extend the idea of the Fourier transform a little bit. So let's say we're doing the Fourier transform of a song or somebody playing the piano. The frequencies, if you've ever studied music, you know, are at certain notes are multiples of each other. And so the frequency is going to change as the song progresses. Now, how do we show that using the Fourier transform? The Fourier transform takes the entire signal from time equals minus infinity to infinity. And so what we're really doing is we're taking all the different frequencies over all of time and then plotting that on the same Fourier transform. And so the answer to that question is we use something called the short time Fourier transform. And so the way that works is it's a two-dimensional heat map, or you can think of it as a contour plot or something similar that shows time on one axis and frequency on the other axis. It shows you different frequency components at different times. And the way it works is it takes the Fourier transform of small windows of time and then moves it along the signal as time goes on. So it's only showing you the frequency spectrum of a small window at each time. Another name for the short time Fourier transform is the spectrogram. So if we look here, there are different function signatures that you could use. Notice that we require the signal processing toolbox if we want to use this method. So spectrogram looks something like this. You have time and frequency, and it shows you how the frequency, the main frequency component, is changing as time goes on. So how do we create, let's say we want to test this function out, how do we create a function that changes frequency as time goes on? So let's say we set x as before. Actually, I've already assigned it. So it goes from 0 to 5 pi, or 0 to 10 pi, and has 5,000 points. So suppose we set the frequency. So a wave looks like this. Frequency times time. So suppose we set the frequency omega, and I'm just typing this out. This isn't real Matlab. Frequency as a function of time is just equal to the time. So we're going to increase the frequency linearly as time goes on. So if we combine those two, we get something like this. y2 equals sine x dot times x, because this is element by element multiplication. Okay, so now I do the spectrogram of y2. And you see that the frequency is increasing linearly, so it takes an equal size step at each window. And notice that there are some artifacts due to the fact that the frequency is not equal within the window that we're calculating the FFT. So you notice that it looked kind of blockish. What you can do is you can pass in the window size along with the data. So let's try a window size of 100. So now you can see it looks much more like a line. So let's try that again with a window size of 500. So now you see the red line is a little bit skinnier, but the time windows are a little bit bigger. And so this is what we call the uncertainty principle. And you may have heard this if you've taken quantum mechanics. The uncertainty principle, when you measure the momentum and it's very accurate, you can't measure the position as accurately. So it's the same when you're taking the Fourier transform, because if we want to know the frequency very accurately, we need to have a very long window of time. But that gives us different frequencies at a lot of different times. If we want to know the frequency at a very specific time, we have to shorten the window. But then we have a frequency that's not as accurate. In this Matlab tutorial, we're going to talk about low-pass filters and how to apply those to an audio stream. So to first recap and kind of give you a different perspective on what we've been doing, we're just going to listen to a sound wave at different sampling frequencies. So I'm going to create my x-axis, 0 going to 50 pi with 10,000 samples. I'm going to say y equals sine x. So this sound is only at one frequency. So it's going to sound like kind of like a buzz. So I'm going to play this sound at a common frequency that's used for recording MP3s and waves, 44,100. So let's listen to this. Okay, and so now what I'm going to do is I'm going to play the same sound wave, but at a lower frequency, a lower sampling rate, and that should give me what sounds like a lower frequency, even though it's the same wave. It's the same matrix of values. And so it indeed sounds lower pitched. And so now what we're going to do is we're going to create a low pass filter. So what that does is, say we have multiple different sine waves playing, which is essentially what the Fourier transform is giving us. We're going to filter the signal so that only the low frequency components can be heard. So if we look at the typical shape of a low pass filter, you'll generally see things like this. And remember that this is only the left half of the plots that we've been looking at. When we're in the frequency domain, convolution turns into multiplication. So right here, 0 decibels is actually equal to 1 because it's a log scale. So we're multiplying 1 by the signal at these low frequencies. But then as we go down here, we're multiplying a very small number by those higher frequencies. And so after we've multiplied one signal by the other, one of them being this low pass filter, those high frequencies are going to be silenced. So if you've never studied about low pass filters before, you may want to go and look up the different kinds, what's their function representation in the time domain and the frequency domain. We're going to use a very simple version of the low pass filter called the moving average. So Matlab already has a function for us that can create filters. We just need to pass in the B and the A, which is essentially the different multipliers on the original signal. Okay, so I'm going to set B to equal 1 over 40 times. I'm going to load my data first. DFS equals audio read hello world.wave. Okay, so I'm going to say DLP equals filter b. So I want 1 as the numerator and then b as the denominator. Pass in the data. So now I want to play the original Hello World for reference. Hello World. And I'm going to play the new low-pass filtered version to compare. Hello World. So you can see you can hear the low-pass filtered version sounds very muffled. Sounds like you're speaking through a pillow or something. And that's because high frequencies tend to not go through different medium. So low frequencies can go through a wall. So if you hear your neighbors talking, for instance, it'll sound a little muffled. And that's the same thing that's happening. Your wall is acting like a low-pass filter. So let's do another way of comparing these. I'm going to plot them on the same axis. It's convenient because they're the same size. So this is D, P. Okay. So now if I zoom in a little bit, so you can see all the sudden changes in the dark green signal don't happen in the light green signal, which is the low-pass filtered version. That's because when you see sudden changes, that's actually, you can think of it as a very fast sine wave that's superpositioned on a low frequency signal. And so we're essentially just getting rid of those. Now yet another way to compare these two signals is to plot them in the frequency domain. So for this we want to use subplots so that they don't overlap each other. So I'm going to just do it all in one line. Okay. So remember that the original signal is on the top and the filtered version is on the bottom. So now you can see that we're keeping the low frequencies, but the high frequencies, which seem to have some components that are non-zero, are all dampened or set to 0 in the filtered version. Now, if you're interested in this, what I would recommend as an exercise is to try to implement a high-pass filter. And as a hint, you're going to want to use the same function filter, and everything else is going to stay the same. So in this Matlab tutorial, we're going to switch gears a little bit to a related topic, image processing. The first thing I want to talk about is, what is an image? So we can compare it to sound waves since we've already studied those. Now let's think about the most raw data possible. So firstly, whereas sound is a one-dimensional function, images are two-dimensional functions. We have an x and a y and a z, and so the z is the value at that x and y. In fact, you can think of a heat map or a contour map as basically images. So we have a 2D function, okay? X and y are continuous coordinates in space. And like with sound, we have to sample the data in order to store it in a computer. So with sound, we're sampling across time, and we call that the sampling frequency. What's analogous to the sampling frequency when we're dealing with images? I'll give you some time to think about that. This is actually probably pretty familiar to you. So with images, the analogous concept would be the resolution, right? So the amount of fine-grainedness you put into each point in space. For example, Udemy videos are required to be recorded in HD resolution. So now let's suppose we have an image called A. A will have the indexes I and J referring to the XY coordinates. I'll just write this down if it helps you. So we have an image A, and then AIJ would be the XY coordinates. So now let's think about what would be stored at AIJ. In other words, how do we store a pixel? So now let's suppose we store just one number at AIJ. So it's a two-dimensional matrix or a table. It's a table of values at each point xy. That matrix would represent a grayscale image, right? Because if we only have one number, we can only represent intensity. So 0 would be black and 1 would be white. And so AIJ would be the intensity at the point IJ. In order to store a color, we need 3 parameters, R, G, and B, or red, green, and blue. And this is what we've been looking at for the entirety of this video so far. So these values usually vary from 0 to 255. So we can have a total of 256 to the power of 3 possible different colors. So let's look at what the value of that is. So that's about 16.8 million different colors we can represent if we store values from 0 to 255 for R, G, and B. Now what this also means is that if we have a 500 by 500 image, the matrix that we use to represent it isn't 500 by 500, but it's 500 by 500 by 3. Sometimes this is called an image bitmap. Alright, so now that we've talked about images in the abstract sense, let's talk about how you would actually open an image in Matlab. So there's an image processing toolbox that we won't be using a lot of in these tutorials. Matlab has a function called IMRead built in. We are going to use that function to read in a very famous picture, often used in image processing. So if you ever take a computer vision course or a multimedia course, you've probably seen this image before. Okay, so let's look at the size of A. So it's 512 by 512 by 3, so a 3-dimensional matrix as promised. Notice the data type is uint8 instead of double that I have for my other matrices, which is the default in Matlab. So a uint8, the U stands for unsigned, int stands for integer, and 8 means it's 8-bit. Okay, so we think about how many values could be stored in a unsigned 8-bit integer. Let's go ahead and calculate that. You should pause this video and try to think about the answer yourself first. Okay, so the answer is 2 to the power of 8, and that's 256. So as we discussed previously, the values for R, G, and B go from 0 to 255, which is 256 different values. there's a function called IMShow that will essentially plot the matrix as an image. So that's the image, the famous Lena image that's used for image processing. So in this Matlab tutorial, we're going to do some basic exercises to just get you working with image matrices, and they're going to be very similar to the exercises we did for sound. So the first exercise I want to do is, how do we flip an image upside down? I'm going to give you a minute to think about that, so please pause this video and then come back when you have figured it out. Okay, so if we want to flip an image, it's going to be exactly the same as we did for sound. So if you recall, a sound was stored in using different samples in different rows, and essentially that's what's happening with an image also, right? So the top of the image is the top of the matrix, and the bottom of the image is the bottom of the matrix. So if we do flip UD, which stands for flip up down, of the image that we loaded, and then we IMShow this image, we see the original image flipped upside down. So now here's something we couldn't do with sound, because sound is one-dimensional, so you can only flip it one way. Now let's suppose I want to flip the image in the horizontal direction. How would I do that? So I'm going to give you a minute to think about that. Please pause this video and then come back when you figured it out. Okay, so if you remember, when we were talking about sound, we looked at two different kinds of flip. There was flip UD, which flipped vertically, and flip LR, which flipped horizontally. So all we have to do is call the other flip function. I'm going to IMShow this flipped image. Right, and so this is the image flipped horizontally. And of course you could flip the image both vertically and horizontally. To get this. Okay, so now the next exercise we're going to do involves working with color. So I've said before that the third dimension in the matrix are the red, green, and blue channels of the color. So how can we show this? So let's say I only want to view the blue channel. How can I visualize that? So I'm going to give you a minute to think about this. Please pause the video and then come back once you've figured it out. Okay, so usually we say RGB because red is the first component, green is the second component, and blue is the third component. So I'm going to assign the original matrix A to a temporary variable B. I want to view blue, so what I want to do is I'm going to set red and green to 0. So how would I do that? I say colon to select all of the rows, another colon to select all of the columns, and then I put a 1 because I want to set the first channel, which is red, to 0. I'm going to do the same for the green channel. And so now only the blue channel has values that are not 0. So if I am show B, now we see only the blue components of the image. Right? And so if I am showed one of the other channels that was set to 0, it's just pure black. So 0 is black, means no intensity at all. So next we're going to look at the green channel. So I'm going to set G equals to A, G colon colon. So I'm setting again red to 0. But now I don't want to set green to 0, I want to set blue to 0. So it's G colon colon 3 equals 0. And I am show G. And so here's the green channel. So it's a little bit more intense, or it has a higher intensity than the blue channel. We can see visually. So now let's say we want to view the red channel. So we're going to do something very similar to the above. So I don't want to set red to 0, I want to set green to 0, which is the second channel. And I want to set blue to 0, which is the third channel. So I am show R, and this is the red channel. So one thing to notice is that no matter which channel we look at, we can still pretty much just view the image. Now why is that? It's because every color contains a red component, a green component, and a blue component. So when you see colors, think of them as sort of a mixture of those three. In this Matlab video, we're going to talk about convolution. So I mentioned this before when we were talking about the low-pass filter, because they're very similar and related concepts. So when we were talking about the low-pass filter, we did a very simple filter called the moving average. And so to give you a sense of what that's doing again, you're taking a window, say 5 samples at a time, and then you're sliding that along the signal and taking the average, and then that is the output of the filter. So this sliding motion and then applying some function to that window that's sliding along is called convolution. So what you're really doing when you're applying a filter is you're convoluting one function with another. So let's look at the definition of convolution. Okay, so convolution is also known as the star operator, and it's the integral of one function with another with this dummy variable. So you can see this sliding motion that I was talking about. Now this won't make a lot of sense to you if you haven't studied calculus before. But there is one important result from convolution, or the study of convolution, that we should talk about and that you should know. And that is that convolution in the time domain, and we use time as a sort of dummy variable, so time can mean actual time or time can mean space. The important distinction is that you're going from time in one domain to frequency in the other domain. So the result that's important is that convolution in the time domain, so if I convolve one signal with another, this is equivalent to multiplication in the frequency domain. So what is the significance of this? So that means there are two equivalent ways of computing the convolution of the signal with its filter. So one way is to just do the convolution using the formula for convolution, which is here. And of course in Matlab, it would be a sum, not an integral, since we have to discretize the signals. But the other way we could do is, since convolution in time is equal to multiplication in frequency, we could take the Fourier transform of both signals first, multiply them, and then do the inverse Fourier transform to go back to the time domain. And so that would be equivalent to doing convolution. One application of this is the Fourier transform, or the Laplace transform, can be used to solve differential equations. So you can solve them in the frequency domain and then convert back to the time domain to get the signal of interest back. So now again, when we think about convolution, a very useful analogy is this sliding motion. And so that's exactly what the moving average was doing. And so one physical manifestation of this is the blurring of an image. And so you'll see in a later lecture that I'm going to do that the blurring of an image is actually convolution, but the sliding motion you can do by hand, and it has the same effect. So this is to say, if you've ever used Photoshop and you've used the blur tool on an image, you notice that you click on the blur tool and you get a point, and then you slide it across the image on the places where you want to blur, and then it blurs those points. Now we're going to move on to the next step in order to implement our blurring tool, or our blurring filter. So the first thing we need to do is we need to extend this idea of convolution to 2 dimensions. So the first modification we did, so we looked at convolution at its most basic definition, where it's of a continuous variable filtered by another continuous variable. So we discretize it by turning it into a sum. And so we already have discrete signals because we're working in Matlab. Now, when we do 2-dimensional convolution, notice we now have 2 dummy variables. So before it was tau or k. Now we have 2 dummy variables, tau1 and tau2, or n1 and n2. And so it's basically what you would expect when you have 1D convolution. You're going from minus infinity to infinity along the one dimension that's the independent variable. So you can think of that as time. And in 2 dimensions, we go from minus infinity to infinity for both independent variables. So that would be x and y, or in other words, the 2 spatial dimensions of the image. Okay, so now that we've extended our idea of convolution to 2 dimensions, let's think about how we could implement a blur using a Gaussian. So a Gaussian is basically a spread, right? There's a middle point, and then it spreads out over a radius in a circular fashion. So my question to you is, how can we build a two-dimensional Gaussian image that we can use as a filter on the original image so that we can do a convolution between those two? So I'm going to give you a minute to think about that. Please pause this video and come back when you've figured it out. Okay, so I have in fact actually been showing you the solution to this for multiple videos now. So I've created a function called myGaussian, and it takes in two parameters, n and sigma. So n is going to be the size of the square, so the output is going to be an n by n matrix, and sigma is going to represent the standard deviation of the Gaussian, as is convention when we're talking about Gaussians. So we have the output called h. Now I only need the value of 2 sigma squared ever in this equation, so I'm just going to calculate two sigma squared at the beginning so I don't have to do that on every iteration of the loop. I'm going to initialize h to be an n by n matrix of all zeros, and then I'm going to use a for loop to assign every value of h. So I going from 1 to n and j going from 1 to n. Now I assign x to equal I minus n over 2 and y to equal j minus n over 2. Why is that? Because I want the center point of h, so that would be h of n over 2, to be the highest point of the Gaussian. And so that's when x is equal to 0 and y is equal to 0, and the exponent of 0 is 1. So that would be the maximum value of the Gaussian, and then every point from there would be smaller, right? So when I is n over 2, x is 0. When j is n over 2, y is 0. And the formula for a Gaussian is x squared plus y squared over 2 sigma squared. And then you take the exponent of the negative of that. Okay, so what does this actually give us? So let's use the myGaussian function. Say n is 100 and sigma is 10. Now let's IM show the h that I got. Okay, so you can see, so remember that white is the maximum value, 1, and black is the minimum value, 0. And so this is a Gaussian, what a Gaussian looks like when you plot it on an image. So what would I do if I wanted to see more white? I could increase sigma, right? So let's say sigma is 25. Now I IM show h. And so you see the radius of the white part has increased. So now let's take our Gaussian and convolve it with the image. So now remember that A is 512 by 512 by 3, which is a 3-dimensional matrix, and H is a 2-dimensional matrix. So if I try to do this, I'm going to get an error. Oh, sorry, we are using the conv2 function, and you still get an error because A is not supposed to be a 3-dimensional matrix, right? So if we look at the definition of convolution, we're working with 2-dimensional matrices if we have 2-dimensional convolution. So what we want to do is, let's just take the red channel, right? It doesn't matter which one, because remember when we were looking at the red, green, and blue channels, we pretty much saw the same image for every channel. Okay, so we still get another warning, and that's that A is still in values of uint 8. So let's change that to double. Okay, so now let's IM show C, see what we get. So it's all white, and so what does white mean? That means all the values are too high, right? So there's too much intensity in this image. So you have to play around with the values a little bit. So let's try making a smaller filter. Okay, so let's say H is equal to my Gaussian 25 and the sigma is 5. I am show C. So now the filter is smaller and the sigma is smaller, so the blur is going to be less, but the intensity is still too high. So that could mean just the values are too high and we need to multiply by lower values. So let's divide the filter values H by 1000. So I am show C again. So now we're starting to see some black, right? So that's good. Okay, so I'm decreasing the values and I'm starting to see the image. Okay, so here is the original image but blurred using a Gaussian of sigma equals 5. Now, one thing I didn't show you guys because I wanted you to go through the exercise of creating a two-dimensional Gaussian filter yourself is that we already have a function called fSpecial in Matlab that creates filters for us. And so fSpecial can create many different types of filters. So in addition to the Gaussian, it can create Laplacian filters, an averaging filter, which is another thing we've used, a Sabel filter, which is useful for finding edges. So all different types of filters. So let's try using fSpecial instead. What was fSpecial? Now let's do our convolution. So I'm going to divide by 1000 because I know I'm going to have to divide. Show C, let's just see what we see. Okay, and so it's a little dark, so I didn't have to divide by 1000. Maybe I could have divided by a lower number. But you can see the idea is that we've blurred the original image using the Gaussian filter given to us by fSpecial instead of our own Gaussian filter that we built. Okay, so like we did before, I want to plot the filter that we created. So I'm going to go IM show little h, which is the filter we created with fSpecial. And notice how it's just all black. Remember that 0 is black and 1 is white. So what we could do, we want to look at what's in H. Let's check the maximum value of H. So max because it's two-dimensional. So the maximum value is 0.0065. So of course, when we plot that, it's going to be pretty close to black. So what we could do, if we wanted to scale it by 1, we want the maximum value to be 1. is we could do IM show h divided by the maximum value. Okay, so now we see what we expect to see, which is white in the middle. So one question you might have is, why is the value of h so small when we use f special? And that's because it does a thing called normalization. So if you have ever studied probability, you know that a probability distribution has to sum to 1. So here it's a similar thing. So if we sum across both dimensions of h, we get 1. And so that's why the values of h are so small. And so now, just for completion's sake, I want to do sort of what's the opposite of blurring. I want to do edge detection of the image. So I want to find all the edges and set those values to 1. So Matlab has a method called edge that will do this, and it's very simple to use. You pass in, again, the grayscale image, right? So only a 2-dimensional matrix. It won't work if you pass in the entire image matrix. Okay, so edge just does all of that automatically for you. So if I IM show E, I can more or less see where all the sharpest edges are. And of course there are parameters you can pass into edge to make it more or less sensitive, but this is by default what it does.
Welcome to this course on MATLAB and probability. This first lecture will focus on the introduction and course outline. Because this course uses MATLAB, it won't follow a traditional probability and statistics course outline. Rather, I'll show you as we go along how the concepts of probability can be applied or viewed through the lens of MATLAB. More generally, I want to show you how a programmer might approach problems in probability. So now let's talk about some of the topics we're going to go through. In the second lecture, we're going to talk about what is probability, and we're going to give some definitions and examples. In the lecture after that, we're going to talk about how we can measure probability given some data. So how to open a file and measure the probability of some of the features of your data. In the next lecture, we'll talk about how do you generate random data? So how can you do a probabilistic simulation? In the next lecture, we'll talk about a famous problem in probability called the birthday problem or the birthday paradox. In the next lecture, we'll extend the idea of probability from discrete variables to continuous variables. In the lecture after that, we'll talk about a special continuous variable distribution called the Gaussian distribution or the normal distribution. In the next lecture, we'll talk about if you have some data that is continuous, how do you test if it is Gaussian distributed? In the lecture after that, we'll talk about if you have two different Gaussian distributed groups of data, how can you compare the two? And then in the last lecture, we'll extend the idea of the Gaussian to a multi-dimensional Gaussian. So what will you be able to do by the end of this course? You'll understand mathematical problems that contain uncertainty. You'll be able to quantify uncertainty, both in theory and in practice. You'll be able to use MATLAB to measure uncertainty in your data. You'll be able to use MATLAB to simulate systems that contain uncertainty. You'll be able to understand and calculate probabilities in the famous birthday paradox. You'll understand the mathematics behind the very famous bell curve or normal distribution or Gaussian distribution. You'll know whether or not the data you're working with is Gaussian distributed. And you'll know how to handle Gaussian distributed data. I look forward to teaching you. Welcome to this third lecture on MATLAB and probability. In this lecture, we're going to stray from your typical probability course. So we're going to have some data matrix, and we're going to measure the probability of a variable that data matrix represents. So what I want you to do is I want you to go to, in your web browser, github.com/lazyprogrammer/matlab-probability-class. Once you go there, you're going to copy and paste this SSH clone URL. Then I want you to go into your terminal and type in git clone and then paste that URL. I've already done it, so I'm not going to do it again. This is going to give you some files that are relevant to this class that I'm going to use for the coming lectures. Okay, so now that you have those files, you want to go into Matlab, change your directory to work in that same directory that you just checked out from Git. Okay, so we're going to load this data. Okay, so R is a 100 by 1 matrix. So let's just plot R. Let's see what it looks like. Right, so it has a bunch of random values that are between -5 and 5. So now let's say I wanted to calculate the probability that R is equal to -5. How would I do that? So one way is I could sum all the values where R is equal to -5 and divide it by the total number of values in R. So that gives me 0.07. I can do the same thing for every other value in the matrix. Right, so we get, about 0.06 to 0.11. So this is what we call the frequentist view of statistics. It means that if we flip a coin 1,000 times, and that's a fair coin with heads or tails, with probability 50%, we should get heads about 500 times and we should get tails about 500 times. The idea is that as the number of coin flips approaches infinity, our measurement of the probability of heads should approach 0.5. Oh, and so we can also plot the histogram of R. And this should give us an idea of the shape of the distribution. Alright, so let's do a little more complex examples. Let's say I want to calculate the probability that R is even. How can we do that? So in the same way as we did before, we might want to say R equals -4 or R equals -2, but that wouldn't be the best way to do this, right? We could use the modulo function. So if R mod 2 is equal to 0, that means R is even, divided by the length of R. Right, so the probability that r is even is 0.43. And we can do the same thing to determine the probability that r is odd. And so notice that these two events are disjoint. You can either have r equals even or r equals odd, and those two events are the only possible events. So their probabilities should add up to 1. And we can verify that 0.43 plus 0.57 is equal to 1. Now, so let's say I want to test if r takes on a specific value. So let's say I want to calculate the probability that r is equal to -5 or +5. How would I do that? So we'd use the OR operator. So r equals 5 or r equals -5 divided by the length of r. So the probability that r is equal to 5 or -5 is 0.21. Notice that we can use this same method for our first problem, which was to determine even or odd. Which is the way I suggested not doing it. But we want to check our answer. And so that gives us the same answer. The probability that r is equal to -4, -2, 0, 2, or 4 is the same as the probability that r is even. So in this class we're going to talk about generating a random variable from a certain distribution. This could be useful for doing simulations of systems that have uncertainty. Matlab has some built-in functions to help us do this. So the first one we're going to talk about is called randi. And it takes one argument called imax. And this function gives us a uniformly distributed variable between 1 and imax. So let's try it. All right, so 9 is in between 1 and 10. Now there's another function, randi, which takes in a maximum value, and another parameter called n. So let's set n to 3. So that returns an n by n matrix of random values between 1 and imax. So suppose I wanted to generate random values between 10 and 20. How would I do that? Because randi can give us values anywhere between 1 and imax. So what we could do is we could just add 10 to all the values that randi returns. So this gives us a 3 by 3 matrix with values only between 10 and 20. Another useful function is just ran by itself. So this function gives us a random number between 0 and 1. So it's different from the previous one where we don't get integers, we get real numbers. Ran returns a number with a uniform distribution. So the probability of getting 0.25 is the same as the probability of getting 0.75. So let's try it and plot histograms for different values of n. Alright, so this is a histogram for random numbers between 0 and 1 for an n equals 10 array. Alright, so it's not quite uniformly distributed. Let's try bigger n though. Alright, so immediately it starts looking more uniformly distributed as n increases. So let's try bigger n. Alright, so it looks even more uniformly distributed now. It's 10,000. Right, so it's almost flat even. It's 100,000. And this is 1,000,000. It looks almost perfectly flat. So that's the idea with the frequentist view of probability, is that when n approaches infinity, your probabilities approach their true values. So now let's think about a different problem. Suppose I want a specific discrete distribution. So say I want to simulate an unfair coin. So to write it out, I want P of heads to equal 0.25, and I want P of tails to equal 0.75. How could I write a function to give me random values that could draw from this distribution instead of a uniform distribution? So we can create a function to do this. I'm going to call it bias coin. It's going to take in one value, little p, which represents the, let's call it p heads, probability of getting heads. And it's going to return the coin face. So we're going to generate a random value. If it's less than p heads, we're going to return heads. Else we're going to return tails. So let's try our function. Alright, so now we're going to try our new bias coin function by initializing an array of, say, size 1000. You know what, we're going to do this in a separate function. We're going to initialize a n by 1 array. We're going to count from 1 to n, and we're going to use the bias coin function to generate a value for each element of the array. So let's try the function we just made. Spice coin 0.25 for n equals 1,000. Alright, so you see number of heads, which resolves to, I think, the integer 104, and then tails resolves to the integer 116. So you see this is about 250 and this is about 750, which is what we would expect in 1,000 coin tosses. One interesting and popular problem in probability is called the birthday problem, or the birthday paradox. And the problem goes something like this. So given a classroom of n students, what is the probability that at least one pair of students shares a birthday? Now you might be surprised that at n equals 23, the probability is about 50%, which is why this problem is called a paradox. So that means in an average sized classroom, there's probably a pretty good chance that two people in the class share a birthday. This is counterintuitive since there are 365 days in a year. In this lecture, I'll show you the theory behind the solution and how to visualize it in Matlab. So the first thing is the problem of at least one pair of people sharing a birthday is difficult. But remember that the probability of all distinct events have to add up to 1. So what is the opposite of at least one pair of people sharing a birthday? It's not two people sharing a birthday or three people sharing a birthday or two pairs of two people sharing a birthday. These events all fit into at least one pair sharing a birthday. So the two disjoint events that we want to talk about are the probability that at least one pair shares a birthday and nobody shares a birthday. So these two events are disjoint and therefore they have to add up to 1. So we can calculate then the probability that two people, or at least one pair of people, shares a birthday as 1 minus the probability that nobody shares a birthday. And so in mathematics, we would call this a counting problem. So now let's think about how do we calculate the probability that nobody shares a birthday. So there are 365 days in a year. Now if you think of each day as a bucket, we have one person and they have 365 buckets to choose from. The probability that this one person will collide with another is 0. The probability that one person shares a birthday with somebody else when there's only that one person is 0. So the probability that nobody shares a birthday in this case is 1, or 365 over 365. Now what about two people? So with one person already having chosen a birthday or a bucket, the second person has a 1 out of 365 chance of colliding with that person. So the probability of at least one pair having a common birthday is 364 over 365. So this is the case with two people. Now if we had three people, the third person only has 363 buckets to choose from. So we have 364 over 365 times 363 over 365. And we can multiply these probabilities because they're independent. So this is the probability that 3 people in a group of 3 people, at least one pair would share a birthday. So we can continue this pattern, but it would probably be easier to write a Matlab function to do this. So my birthday function is going to return all the probabilities up to the value n. So I'm going to initialize a to be an array of zeros, and I'm going to count up to n and fill in the values of a. Actually, I'm going to say ones because we're subtracting from 1. Actually, doesn't matter what I initialized a to, because I'm going to say 1 minus over here. Okay, so we know that we have to multiply by something over 365 each time and subtract that from 1. And so we can use a for loop to iterate over the thing that has to be subtracted and multiply the new value iteratively. Now that we have our function, let's test it. So let's say a equals birthday, and let's set n equal to 100. And let's plot a. So you can see here, when n is about 23, you get the probability around 0.5. When n is equal to 50, you're at above 90%. So there's a pretty good chance in a group of 50 people that at least one of those pairs of people shares a birthday. So let's check A23, right? It's about 50%. And that is the solution to the birthday paradox. In this lecture, we're going to talk about continuous variables. So we've talked about discrete variables up till now. Discrete variables can only take on distinct values, but continuous variables can take on any value. So with continuous variables, we don't have a notion of probabilities for exact values because x can take on an infinite number of values. So the probability of equaling any specific exact value is 0. We can have probabilities for ranges though. So for example, we can say the probability of x being between 3.13 and 3.15 is greater than 0. We have a useful function called the cumulative distribution function, or the CDF, that helps us measure such probabilities. We usually label this function as big F of x. And so the definition of big F of x is it's the probability that the random variable big X is greater than negative infinity, but less than little x. Note that the probability of big X being between negative infinity and positive infinity is 1, since x has to take on a value. Therefore, the value of big F of positive infinity is equal to 1. Now how about going back to our original problem if we want to calculate the probability that x is between 3.13 and 3.15. That would just be big F of 3.15 minus big F of 3.13. So now let's talk about the other useful function when we're talking about continuous variables. This one's called the probability density function, or the PDF. We usually denote it by little f of x, and it is defined as the derivative of big F of x with respect to x. So it's like the slope of big F of x. Note that this function can be greater than 1 since it's not a probability. It is a probability density. F of x, little f of x, does have to be greater than or equal to 0 though. So here's one example where little f of x can be bigger than 1. So let's say little f of x is uniform between 0 and 0.1. So that means if you try to sample from this random variable x, you'll always get a value between 0 and 0.1, and the probability of any particular value is equal to all the others. Now I'm going to claim that little f of x has to equal 10 if x is between 0 and 0.1 and 0 otherwise. Now why is this? Because big F of x, since little f of x is the derivative of big F of x is the integral of little f of x. In the integral, we can take the constant out and then calculate the integral from 0 to x. Now we know that from above, big F of infinity has to equal 1. So the integral from minus infinity to infinity equals to 1. But since little f of x is 0 after 0.1, we can just take the integral from 0 to 0.1. That gives us 0.1c. And if we solve for c, c equals 10. Therefore, we've seen a scenario where little f of x can have a value greater than 1 because it's a probability density and not a probability value. Later on in this course, we'll look at more complex continuous distributions. In this lecture, we're going to talk about mean and variance. So how do we measure the distribution of continuous variables? We know that with discrete variables, we can just check how often your random variable takes on a certain value and divide it by the total number of values to give you an approximation or an estimation to that value's probability. But we can't exactly do that with continuous variables. We can't really count them and put them in the buckets like discrete variables. So we need to measure certain characteristics of the distributions that might tell us the shape of their distribution curve. So two common measures that you probably have already heard of are the mean and the variance. So first let's talk about the mean. So the mean is like the average. It means you add up all the different values and you divide it by the total number of values, and that kind of tells you what the middle value would be. So what I want you to do is to load back up our random integers CSV. And so you know how to calculate the sum of all the values. And we want to divide this by the total number of values. So the mean of R, so let's just plot R again to remind ourselves what values it can take. So minus 5 to 5. And so we get an average value of 0.35. So why is this value so small? Because we generated values from -5 to 5 with a uniform distribution, we could say that the distribution is balanced whether the value is less than 0 or greater than 0. So a lot of the numbers end up canceling each other out when you sum them, and therefore our mean value is about 0. Notice that we can never actually get the value 0.35 from our distribution, right? Because our distribution gave us uniformly distributed numbers between -5 and 5, but only with discrete values. So you could get -5, -4, -3, -2, -1, or 1, all the way up to 5, but you would never get the value 0.35. So it might seem odd that we also call the mean value the expected value, even though we would never expect to get that actual value. We only expect that to be the average value of the values that we do draw from this random distribution. And of course, there's an easier way to calculate the mean in Matlab, and it's just the function mean, right? And so we get the same value. Now let's talk about the second measure of distribution variance. So we already talked about the mean, which is kind of like the middle value. So we could say that it measures the centeredness of the distribution. So where the middle is, where the center is. Variance does a different thing. It measures the spread. So one thing tells us where the random variable goes, and that's the mean. And then the variance tells us how much it's spread out from that middle value. So the definition of the variance is it's the expected value of the random variable minus its mean, and then we square that whole thing. And of course that doesn't help us much, since it doesn't tell us how to calculate or estimate the variance. But it's very similar to how we do the mean. So let's set the mean of R to be mean R, like that. We can then calculate the variance of R by taking R minus the mean of R. And so we want to do the dot product between these two, which is effectively squaring all the individual values and then multiplying by the corresponding value, like that. So it's treating R as a vector and then finding the dot product with itself after subtracting the mean. In other words, it's like subtracting the mean and taking the squared distance, or the squared length. And of course we divide by the length of R. So we get 10.6475. Of course Matlab has its own variance function, so we didn't really need to do all this work. And it's just var. So we get a pretty similar value. One thing that comes up in statistics, which is a little bit outside of the scope of our discussion, is that if we divide, instead of by n, we divide by n minus 1, that gives us what we call an unbiased estimate of the variance. And so this gives us the exact value of MATLAB's version of var. In this lecture, we're going to talk about a special continuous distribution called the normal distribution or the Gaussian distribution. It probably looks very familiar to you, since it is what most people refer to as the bell curve, and you've probably seen this in school, where bell curves are used to shift marks up or down based on how well students perform. So this formula you see here is the PDF of the Gaussian distribution. Notice how they also use the little f notation on Wikipedia. The interesting thing about the Gaussian distribution, so we talked about last time that the mean and the variance are two special numbers that help us describe what a continuous distribution looks like. With the Gaussian distribution, the mean and the variance completely describe the shape of the distribution. So the mean tells us where the center peak is of the bell curve, and the variance tells us how much that bell curve is spread out. So you can see this yellow curve is very spread out, and the blue curve is spread out not that much. So let's talk a little bit about this formula. First, there is a normalizing constant. It's 1 over the square root of 2 pi times sigma, which is the variance. Actually, sigma stands for the standard deviation. Usually it's written as 1 over the square root of 2 pi sigma squared, where sigma squared goes inside the square root. So sigma squared is the variance and sigma is the standard deviation. Second part of the PDF is this exponential. So we take the negative of x minus the mean, which we denote by mu, square that, divided by 2 sigma squared, or 2 times the variance, and then we exponentiate that. Note that since we square the thing where x is, this PDF is symmetric. So if you go a distance from the mean to the left, or that same distance to the right, you will get the same value for the PDF. So let's do an exercise where we plot the values of a Gaussian curve from, say, minus 100 to 100. So we'll create a new function, call it myGaussian. We'll take in 2 parameters, mu and sigma squared, and we'll output an array. And so n will be the number of different values between min x and max x. So we're going to start our little x value at min x, and then we want to know how much to increment x on each iteration of the loop. So we'll call that dx, and we'll say it's max x minus min x divided by n. So at the end of the loop, we're going to add dx to x. We're going to call this f. Okay, so we're going to return let's return the array of x values also. So x of I is going to equal 2x, and f of I is going to equal 2. So return x and f. So 1 over the square root of 2 pi sigma squared times exponential of negative x minus the mean squared divided by 2 times sigma squared. So let's do this for mu equals 0, sigma squared equals 1. Let's say minus 10 to 10, and then have 1,000 values between them. Okay, so now we can plot x and f. Alright, so we get this bell curve. So the peak is at 0 because that's the mean, and then it's spread out and from about -2 to 2. So the drop off, or how fast f of x goes to 0, is pretty quick. You can see the maximum value is about 0.4. Let's try that again with a smaller variance and some smaller values also of min x and max x. So let's do 0.1 for the sigma squared. Let's plot it again. Alright, so the drop off is even quicker now, where we get to about 0 at -1 and 1. And notice the peak value is above 1.2. So since this is a PDF, values above 1 are allowed. In this lecture, we're going to talk more about the Gaussian distribution. So the first thing we'll ask is, we've generated data so far from uniform distributions. How can we generate data for random normal distributions? So there's a function in Matlab called randen that will do this. So if you type in randen, should give you different function signatures. So let's say we want to generate 1,000 random normal values. Okay. And so this can represent any number of random values. So if you download data from Kaggle or some other data set where you want to do machine learning or statistics on, you want to know the distribution of your input. In this case, we want to know if the distribution is normal or not. So one thing we could do to check that is just to plot the histogram. Right, and so you can see that it looks relatively normal. We can use more bins to get a finer granularity. Right, so we still see this same type of distribution even with 50 bins. And of course, if we increase n, our curve looks closer and closer to the Gaussian curve that we saw from the last lecture. Now, of course, in the real world, your data is not going to look this nice and clean, since your distribution may or may not be Gaussian distributed. The question now is, how do you test if your data is Gaussian distributed or not? So we're going to talk a little bit about hypothesis testing, but not too much, since it's a pretty long and difficult subject. So the basic idea with hypothesis testing is you have two different hypotheses. So in this lecture, we're not going to talk about the mechanics behind statistical testing. We're going to kind of work backwards and jump right into statistical tests that you can use in Matlab right away. So the first is the Jacques-Barré test. In Matlab, it's the function JB test. So you can use it to return a hypothesis and a p-value. The hypothesis will be whether or not your data is randomly distributed, and it returns a p-value to tell you the strength of that hypothesis. So let's try this on our data that we just generated. Alright, so one thing that we need to talk about is how to interpret the return values of the Jacques-Barré test. So when we talk about hypothesis testing, you'll see that there is a null hypothesis and an alternative hypothesis. The Jacques-Barré test will return 1 if we reject the null hypothesis, and the null hypothesis is that our data is normally distributed. All right, so if we pass in R, we get the hypothesis is the null hypothesis and a p-value of 0.5, which means we do not reject the null hypothesis that our data is normally distributed. There's another test called the Kolmogorov-Smirnov test, which essentially does the same thing. So the null hypothesis again is that the data comes from a normal distribution, and the result H will be 1 if you reject the null hypothesis. So let's try that. Same thing with KS test. Right, and so this also rejects, or does not reject, the null hypothesis that the data is normally distributed. So now let's do something interesting. Let's generate some random data that we know is not normally distributed. So we'll do this data from a uniform distribution. So now I want to do JB test on the uniform data, right? And so we get H equals 1, which means we do reject the null hypothesis, and our p-value is 1/1000th. And usually a p-value is determined significant when it's less than 5%. So what this is basically saying is that our uniform generated data is not Gaussian distributed, which we know already is true. We can do the same test with Kolmogorov-Smirnov. And so this also rejects the null hypothesis with a much smaller p-value. Right, and so this is how you can test if your data is normally distributed or not. In this lecture, we're going to continue our talk about hypothesis testing of Gaussian distributed data. So to elaborate on how hypothesis tests work, we're going to talk about the hypotheses a little bit more. So there are two hypotheses when we're doing a statistical test. There's a null hypothesis, which we call H0, and it usually represents the control data or random data that results purely from chance. The second hypothesis is the alternative hypothesis. So this is the thing we're trying to prove generally. For example, if we're doing an experiment where we're testing a drug, the drug actually working would be the alternative hypothesis. And so the alternative hypothesis is the hypothesis that sample observations are influenced by some non-random cause. So now suppose we have some random data. So let's say R1 equals rand_n. Say it has 100 points with a mean of 0 and a variance of 1. Now let's say we have another data set, which is maybe 20 points. But this one's going to have a different mean. So let's say its mean is 1. And let's increase its variance a little bit. Okay, so we have two distributions that are Gaussian distributed. The first one has 0 mean and 1 variance. The second one has a mean of 1 but a standard deviation of 2. So how do we compare these two distributions? There's a test called the t-test, or the two-sided t-test, or the two-sample t-test, which does what we want. And it again returns a hypothesis and a p-value. So we can try this. T-test 2. Okay. So we reject the null hypothesis in this case with a very, very small p-value. Remember, it only has to be less than 5% for us to reject the null hypothesis. So let's try some things. Let's have less data points for R1. Okay, and let's do our t-test again. So notice how we still reject the null hypothesis, but our p-value has increased, so it's less significant than before. Alright, so now let's do the same thing for R2. Let's say this now only has 10 points. Let's do the t-test again. Alright, so this is still significant. Let's increase the variance. Alright, so I had to increase the variance a lot to get an insignificant p-value. So that's one thing about when you're comparing two Gaussian distributions. You can't really say one is bigger than the other if they're spread out a lot. So let's put the variance back for R2. But let's say the mean is now less far away from R1's mean. Let's do our t-test again. Right, so this also gives us an insignificant p-value. So that's another fact about the t-test, is you also can't tell if two distributions are different if they are very close together. If they're very far apart, so the mean is, let's say, we do the t-test again, we now get a very small p-value. In this class, we're going to talk about the multivariate Gaussian. So in all our past lectures, we've looked at the one-dimensional case. So one-dimensional distributions, both discrete and continuous. When we talk about the multivariate Gaussian distribution, we're talking about two or more dimensions. And of course, Matlab is perfect for this because it works with all matrices and vectors. So now what happens when you extend the Gaussian like this? So the first thing is that the mean becomes a vector. And again, this doesn't really change the definition of the mean. You still add up all the values of x and divide by n to get your sample mean. So as an example, let's say we have a random matrix with 100 values and with 10 dimensions. Right, so if we do mean x, we get a 1 by 10 matrix, and each component is the 100 values in that column summed up together and divided by 100. The thing that is kind of more different than the one-dimensional case is the variance. So we see this sigma symbol here, and what this stands for is the covariance matrix. So with the variance, it told us how far x was spread out from the mean. And the covariance does that too, but only on the diagonals. So on the off diagonals, it tells us how correlated one dimension is with the other. And so you can see here the definition of the covariance matrix is the covariance of the ith dimension with the jth dimension, and that would be the ijth element of the covariance matrix. We don't really need to worry about how to calculate it because we are in the end going to end up using the Matlab function cov. So let's check that covariance is 10 by 10. So our dimensionality is 10. What's interesting about the PDF of the Gaussian in the multi-dimensional case is that we never use the covariance directly. We use the inverse right here in the exponent and the determinant. And again, since we already wrote a function to calculate Gaussians before, I'm not going to ask you to do it again. There's already a function called MVN PDF in Matlab that will do this for you. So I've got an example here that I want to show you. We set our mean and our covariance. Don't worry about this code too much, since it is not the focus of this lecture. We're simply setting the x-axis, so the x1 and x2 values. Note that the dimensionality of x is 2. So mu is 2-dimensional and sigma is 2 by 2. So here we calculate the PDF value using MVN PDF. And we're going to do a surface plot of f versus x1 and x2. So now some points worth talking about is this distribution is more spread out on the x2 axis than the x1 axis. And that's because you see here this distribution has a variance of 1 on the x2 axis, but a variance of 0.25 on the x1 axis. And since the off diagonals are not 0, what we get is a Gaussian that is not perpendicular to the x1 and x2 axes.